Hello there and welcome to Physics with William. Where curiosity gets cozy, the universe lowers its voice a little, and even the strangest corners of science are allowed to take the scenic route towards sleep. Tonight we are drifting into a part of physics that sounds, at first, like it belongs in a magic show, a haunted observatory, or perhaps a very confident conversation between two theoretical physicists who forgot to explain the first sentence. We're going to talk about virtual particles. Those odd little visitors that appear in the mathematics of quantum theory seem to do useful work, help describe forces, shift measurable quantities, and yet are often described by physicists with a phrase that sounds almost rude. They are not real. Now that is a curious thing to say about something that changes reality. Usually if something is not real, we do not expect it to leave fingerprints. A pretend cat does not knock over a real vase. An imaginary spoon does not stir actual tea. A fictional pigeon, no matter how determined, does not land on your windowsill and demand crumbs. And yet in physics, virtual particles occupy this strange middle ground. They are not particles in the ordinary sense. You cannot trap one in a jar. You cannot point a detector at empty space and wait for a virtual particle to wander in wearing a small name tag. They are not little beads popping in and out of existence in the same way dust motes drift through sunlight. And still, when physicists use them carefully, they help explain effects that can be measured with astonishing precision. So tonight, we're asking a question that is simple enough to say but deep enough to keep entire departments politely disagreeing over coffee. If virtual particles are not real, why do they change reality? Before we ease into that puzzle, I would love to know where you're listening from tonight and what sort of quiet surrounds you at this moment. Is it late evening where you are, with the room settling into that soft hush that only arrives after a long day? Is it morning perhaps, with the world not yet fully awake and the kettle making its small patient sounds? Or are you somewhere in between, borrowing a little pocket of calm from a busy afternoon? It is a fitting question, really, because virtual particles live in the strange boundary between what is directly seen and what is inferred, between what appears in our mental picture and what survives in our measurements. And here you are too, in your own little part of the world, present to yourself in a way no instrument can fully capture. If you find this gentle journey soothing, interesting, or simply a pleasant place to rest your thoughts for a while, I would be very grateful if you liked the video and subscribed. It helps this quiet little corner of physics reach other tired minds who might enjoy a soft landing among atoms, fields, forces, and the occasional deeply suspicious empty vacuum. And as always, I hope the science is interesting enough to keep your imagination warm, but not so interesting that it keeps you awake. If it does, well, at least you will have spent the time in good company, with a universe that is stranger than expected, but not in any hurry to explain itself all at once. So settle in. Let your shoulders drop a little. Let the day loosen its grip. We are going to begin not with the most advanced machinery of particle physics, but with something far more familiar. Empty space. At first, empty space seems like the easiest thing in the world to understand. It is simply the place where nothing is. Take away the stars, the planets, the gas, the dust, the stray sandwich crumbs from a careless astronaut, and surely you are left with nothing, a clean blankness. A cosmic room after the furniture has been removed. This is how the vacuum was often imagined for a long time, as an absence, a silence, a stage after the actors have gone home. But in modern physics, empty space is not quite so empty. It is more like a quiet sea whose surface appears flat only from far away. Look closely enough, and the stillness has texture. This does not mean that space is packed with ordinary particles hiding in the dark. It means that the basic ingredients of modern physics are not little solid objects sitting inside space like marbles in a box. Instead, the deeper description speaks in terms of fields. A field is something that has a value everywhere. That may sound rather dry, like the sort of definition that quietly removes all joy from a room, but the idea is actually quite gentle. Imagine the temperature in your bedroom. Every point in the room has some temperature, even if you're not measuring it. Near the window, it may be cooler. Near a lamp, it may be warmer. The temperature is not a particle. It is a condition spread through space. A field is somewhat like that, though usually far less likely to make you reach for a blanket. In quantum physics, every kind of particle is understood as an excitation of a field. An electron is not a tiny hard pellet that exists separately from everything else. It is a stable ripple in the electron field. A photon, the particle of light, is a ripple in the electromagnetic field. Other particles arise from other fields. The universe, in this view, is not built from little objects moving through empty nothingness. It is built from fields that can vibrate, interact, transfer energy, and produce the particle-like events we observe. It is less like a stage filled with actors and more like a vast collection of instruments, each capable of producing notes under the right conditions. Now, here comes the important part. Even when a field has no real particles in it, it is not completely inactive. Quantum fields do not sit perfectly still. The vacuum is the lowest energy state of those fields, but lowest does not mean motionless in the familiar sense. It means as quiet as quantum rules allow. And quantum rules are not fond of perfect stillness. They leave a faint restlessness in the background, a kind of unavoidable uncertainty built into the fabric of fields. This is where many popular explanations introduce the image of particles constantly popping into existence and disappearing again. It is a memorable picture. It is also a picture that needs careful handling, because it can mislead us if we take it too literally. Virtual particles are not tiny objects that borrow energy from the universe, dash around for a moment, and then vanish before anyone notices the missing coins from the cosmic till. That image is charming, and it gives us something to visualize, but it is not quite what the mathematics says. In serious physics, virtual particles are not observed particles. They are not directly detected arrivals. They appear inside calculations as a way of organizing how fields interact. They are internal pieces of a mathematical process, not free-travelling things that begin and end like ordinary particles. This may sound disappointing at first, rather like being told that the mysterious footsteps in the attic were only the heating system. But actually it is more interesting, because sometimes the things that are not real in the plain everyday sense are still indispensable in describing what is real. A map is not a landscape, but it can guide you across a country. A musical score is not sound, but it can allow an orchestra to fill a hall. A weather model is not a storm, but it can tell you when to bring an umbrella. Virtual particles are a little like that. They are not real particles flying around in the way electrons or photons can be, but the framework that uses them can predict real effects, often with extraordinary accuracy. The trouble is that the word real is doing a lot of heavy lifting here. In everyday life, real usually means something we can touch, see, photograph, or at least trip over in the hallway. In physics, reality is more subtle. Some things are real because they are directly detected. Some things are real because they produce consistent measurable effects. Some things are real because they are part of the best explanation we have, though not observable on their own. And some things are useful mathematical tools that should not be mistaken for objects, even though removing them from the calculation would make the explanation collapse like a poorly assembled deck chair. Virtual particles live in that last neighbourhood. They are useful. They are powerful. They show up whenever quantum fields interact. But they do not satisfy the usual requirements for being ordinary particles. A real particle has a definite relationship between its energy, momentum, and mass. It can travel from one place to another and be detected as an actual event. A virtual particle does not have to obey the same condition while it is inside the calculation. It is part of the exchange, part of the bookkeeping, part of the unseen internal machinery that helps us compute what real particles will do. That word bookkeeping might sound a little unromantic, but physics is full of bookkeeping. Nature does the happening. Physicists try to keep accounts. When two electrons repel each other, for example, we know there is an electromagnetic interaction. In a quantum field description, We can calculate that interaction by describing the electrons as exchanging virtual photons. The virtual photon is not a little flashlight beam tossed from one electron to the other. It is not a tiny glowing messenger with a brief employment contract. It is a term in the calculation that captures how the electromagnetic field mediates the interaction between charged particles. The result of the calculation tells us something real. The electrons scatter in a particular way. The probabilities match experiments. The force behaves as expected. The virtual photon is part of how we describe the process, but not something we catch in isolation. This is one reason the question becomes so interesting. If virtual particles are not real in the ordinary sense, how can they be said to cause anything? Maybe they do not cause things in the simple billiard ball sense. Maybe they are not tiny agents pushing and pulling behind the curtain. Instead, they represent the structure of interactions in the quantum fields, and those interactions are undeniably real. The effect is real. The measurement is real. The virtual particle is a way of calculating the influence. It is a picture, not the furniture itself. But pictures matter. Humans are not equations with pajamas. We need images. We need stories. We need some way to think about invisible processes without melting quietly into confusion. So physicists often use virtual particles as a kind of language. It is a language that works beautifully when used properly, but like any language, it can be misunderstood. If someone says the sun rises, we do not usually stop breakfast to complain that the earth is rotating. We understand what the phrase means in context. In the same way, when physicists say virtual particles appear and disappear, they may be speaking in a shorthand that helps describe fluctuations and interactions, not making a literal claim about tiny particles blinking into being like shy fireflies. This is especially important because the vacuum does produce real measurable effects. One of the most famous is the Casimir effect, where two very close uncharged metal plates in a vacuum can experience a tiny attractive force. A common explanation says that virtual particles outside the plates push more strongly than those between the plates, drawing them together. That picture is useful, and it can be made to give the right intuition, but the deeper story is about changes in the allowed modes of quantum fields between the plates. The plates alter the conditions for the fields, and the vacuum energy differs in a measurable way. The effect is real. The virtual particle description is one way of talking about the field behaviour. The plates move, not because cartoon particles are banging on them like impatient delivery workers, but because quantum fields respond to boundaries. Another example is vacuum polarization. Around a charged particle, the quantum vacuum behaves as if it can be slightly distorted. The presence of charge influences the surrounding fields, and this changes how the charge appears at different distances. In a diagrammatic picture, virtual particle pairs briefly appear and screen the charge. Again, if we take the image too literally, we may imagine small particles bubbling up from nowhere, forming a temporary crowd around an electron, and then politely leaving. But the more careful statement is that quantum fields modify the interaction. The vacuum is not inert, it responds, and that response changes measurable quantities. Here we begin to see the heart of the matter. Virtual particles do not need to be real objects in order for the calculations involving them to reveal real changes. They are like the hidden scaffolding in a construction plan. Once the building stands, you may never see the scaffolding as part of the final structure, and perhaps some of it was only part of the drawing process, but without the scaffolding or the plan that included it, you would not understand how the pieces came together. The reality is in the final measurable structure. The virtual particles are in the method we use to describe the work that cannot be seen directly. This can feel unsatisfying because our minds prefer simple categories. Real or unreal, there or not there, particle or not particle. But quantum theory has a habit of making these categories less tidy. An electron is real, yes, but it is not a tiny planet. A photon is real, yes, but it is not a miniature bullet of light in the everyday sense. A field is real, but not as a solid substance. The vacuum is empty but not inactive. Virtual particles are not real particles, but they are not meaningless either. They are mathematical features with physical consequences when used as part of a theory that accurately describes the world. A gentle way to hold the idea is this: virtual particles are not things you can observe directly. They are things that appear in our descriptions of how observable things interact. They do not change reality by acting like little hidden marbles. Rather, they are part of a successful language for calculating how quantum fields change reality. And since quantum fields are the working fabric of particle physics, that language matters very much. Think of watching ripples on a pond at night. You may not see the fish beneath the water, or the small stone that fell earlier, or the shape of the pond bed below. But you can see the pattern on the surface. You might create a model to explain how waves move through that pond. Some elements of the model are not things floating on the water. They are methods for describing the motion. They help predict where the ripples will go, how they will overlap, and where they will become stronger or weaker. If the model works, it tells you something real about the pond, even if not every piece of the model corresponds to a separate object you can scoop out with a net. Quantum field theory is far more precise than a pond, of course, and also far less likely to contain frogs. It is among the most successful frameworks ever developed in science. Some of its predictions agree with experiments to a level of precision that feels almost unreasonable, like measuring the distance from your pillow to the moon and being worried about the thickness of a hair. The use of virtual particles inside this framework is not a whimsical extra. It is deeply woven into the way physicists calculate interactions. But precision does not automatically mean that every mental picture is literal. That is the delicate lesson. The phrase "not real" can also be a little unfair, depending on what someone means. If by real we mean independently detectable as a free particle, then virtual particles are not real. If by real we mean appearing as stable objects that can arrive in a detector, then no, they do not qualify. But if by real we mean part of a calculation that corresponds to measurable physical effects, then they are connected to reality in a strong way. They are not fantasy. They are not decoration. They are not just mathematical confetti thrown into a paper to make it look festive. They are part of the machinery that lets theory meet experiment. This is why physicists sometimes speak cautiously. They may say virtual particles are not real, then use them constantly. This can sound contradictory from the outside, rather like saying a ladder is not real while climbing it to clean the gutters. But the point is that the ladder in this case belongs to the description, not necessarily to the ontology. Ontology is just a fancy word for what exists, and it tends to make conversations sound more expensive than they need to. The practical statement is simpler. Virtual particles are tools in our best calculations, not little objects we should imagine too literally. Still, there is a beauty in the fact that the vacuum is not dull. Empty space, once imagined as nothing at all, turns out to be full of structure. Not full in the ordinary sense, not crowded like a train station, but rich with possible activity. Fields extend everywhere. Interactions happen through those fields. Boundaries change what the fields can do. Charges disturb them. Forces arise from them. The universe is not sitting on a background of blankness. It is made of restless ingredients, even in its quietest state. And this brings us gently back to the question waiting at the center of tonight. If virtual particles are not real, why do they change reality? Perhaps the answer begins by replacing the question with a more careful one. Why does a mathematical description involving virtual particles predict real effects? And the answer is that virtual particles represent the possible internal ways quantum fields can interact. They are not directly observed things, but they encode real relationships. They help calculate how particles scatter, how forces operate, how the vacuum responds, and how measurable quantities shift. They change reality only in the sense that the underlying quantum fields change reality. And virtual particles are one of the languages we use to describe that change. That may sound less dramatic than particles flickering in and out of being, but it is actually more stable and more profound. It means reality is not built only from what can be directly seen. It is also built from relationships, constraints, fields and patterns of interaction. The invisible does not have to be imaginary. The mathematical does not have to be empty, and the useful does not always have to look like a tiny object flying from one place to another. So as we move deeper, it will help to keep two ideas beside us, like a pair of small lanterns. First, virtual particles are not real particles in the same way electrons and photons can be real particles. They are internal features of calculations, not directly detected objects. Second, the effects described with virtual particles can be real and measurable because they come from the behavior of quantum fields themselves. The mistake is not using virtual particles. The mistake is imagining them too literally, as if the vacuum were a bubbling soup of little temporary beads. The truth is quieter, stranger, and in some ways more elegant. The next step is to understand what physicists really mean when they call something virtual, because the word itself carries a bit of everyday baggage. Virtual can mean almost real, simulated, online, artificial, or not quite there. But in quantum theory it has a precise role, and that role has less to do with fakery and more to do with how interactions are represented. The universe is not playing pretend. Our language is simply trying to follow processes that are too small, too fast, and too deeply woven into fields to be pictured in the ordinary way. And somewhere inside that careful language, these so-called unreal particles keep guiding us toward very real results. To understand why physicists ever started talking about virtual particles at all, we have to spend a little more time with the vacuum, because empty space is one of those ideas that seems simple only until science leans closer. At ordinary scales, emptiness is easy to picture. An empty glass has no water in it. An empty room has no people in it, unless someone is hiding behind the curtains, in which case the problem is less physics and more manners. Empty space, by this everyday way of thinking, should mean a place with nothing inside it. No air, no dust, no light, no drifting atoms, no invisible mist of anything, just a plain absence. That picture is useful in daily life. If you pump the air out of a sealed chamber, you have made a vacuum, or at least something close enough for many practical purposes. Engineers, chemists, and experimental physicists use vacuums all the time. A good vacuum can keep particles from bumping into each other when you want a clean experiment. It can let delicate beams travel without interference. It can make certain machines work properly. In that sense, a vacuum really is a region where nearly all ordinary matter has been removed. It is empty compared with the crowded, restless air around us. But when quantum physics enters the room, emptiness stops being a simple absence and becomes a state. That is a subtle change, but it matters. In modern physics, the vacuum is not just what remains when we remove particles. It is the lowest energy condition of the fields that fill space. Those fields do not disappear when particles are absent. They remain. They are the underlying systems from which particles can arise. If a particle is like a wave on a sea, the field is the sea itself. Removing the waves does not remove the water. It only leaves the surface as calm as it can be. The difficulty is that in quantum theory, as calm as it can be does not mean perfectly still. A quantum field in its lowest energy state still has a kind of built-in restlessness. This is not restlessness like nervous pacing or a kettle about to boil. It is not motion in the ordinary sense. It is a consequence of the way quantum systems are described. At very small scales, physical quantities cannot always be pinned down with unlimited precision. A field cannot be forced into a condition where everything about it is perfectly settled. There is always some irreducible uncertainty in the background. This is where the popular image of flickering particles begins. People say that the vacuum is full of particles popping in and out of existence. They say empty space is bubbling with temporary pairs, appearing for a tiny moment and disappearing again. It is a vivid picture, and it has helped many people get a first feeling for quantum vacuum behavior. It makes the vacuum sound alive, like a dark pond with small bubbles rising from below. But it also creates a problem, because it can make virtual particles sound like ordinary little things that briefly exist and then stop existing. That is not quite right. A better first step is to say that empty space has fluctuations. A fluctuation is a small variation from perfect stillness. In a classical picture, if nothing is happening, nothing changes. In a quantum picture, even the lowest energy state of a field contains unavoidable variations. These variations are not random little particles in the familiar sense. They are changes in the possible values of the field, spread through the field itself. They are part of what it means for a quantum field to exist in its ground state. The word flicker can still be useful, as long as we hold it gently. It gives the right feeling that the vacuum is not dead and flat. It suggests that there is activity beneath what appears empty. But the flicker is not like a spark that a camera could catch if the shutter were fast enough. It is not a tiny flash of matter in a hidden background. It is more like the field refusing to be described as exactly zero in every possible way at once. The vacuum is quiet, but not blank. One reason this is hard to picture is that ordinary human intuition was trained in a world of objects. Chairs are either in the room or not in the room. A biscuit is either on the plate or has already been eaten, often under suspicious circumstances. If something affects something else, we expect there to be a direct object doing the affecting. A hand pushes a door, wind bends grass. A ball strikes a window, followed by a very brief pause in which everyone nearby becomes deeply interested in clouds. Cause and effect usually come with visible things moving through visible space. Quantum fields do not always cooperate with that style of thinking. In the quantum field view, particles are not the deepest objects. Fields are. Particles are excitations of fields. When the field carries energy in the right way, we can observe a particle. When it does not, the field is still there. So the vacuum is not a box with all the marbles removed. It is the quietest possible arrangement of the systems that can produce marbles when excited. That quiet arrangement still has structure, and structure can matter. A helpful comparison is a musical instrument sitting silently in a room. A violin that is not being played is not producing a note. No melody is coming from it. Yet the violin has a structure. Its strings have tension. Its wooden body has shape. Its bridge and air cavity determine what kinds of sounds it can produce when played. Silence from a violin is not the same as the absence of a violin. In a similar way, a quantum field with no real particles is not the same as no field at all. It has a silent structure, and that structure affects what can happen. This is important because the vacuum can respond to conditions, put boundaries in it, such as metal plates placed extremely close together, and the possible behavior of fields changes. Place a charged particle in it, and the surrounding fields behave differently from how they would with no charge present. Arrange particles to scatter from one another, and the fields mediate their interaction. The vacuum is not a passive nothing that merely waits for events. It is the baseline condition of the fields through which events happen. Still, it is worth being careful with the word energy here. People sometimes hear that the vacuum has energy and immediately imagine a limitless power source hidden in empty space, which is the sort of idea that tends to attract both science fiction writers and people selling very strange machines in badly lit videos. Vacuum energy is real in the sense that quantum fields have a ground state structure, and that differences in vacuum energy can have physical effects. But it is not a simple fuel sitting there waiting to be scooped out. The vacuum is not a cosmic battery that someone forgot to lock. In physics, extracting useful work from a system requires more than the presence of an energy scale. It requires differences, conditions, constraints, and a way for energy to flow in a controlled manner. The strange flickers beneath empty space are therefore not a free lunch. They are not little packets of usable energy, appearing conveniently for anyone with a clever enough plug. They are part of the quantum description of fields. They show up most clearly when we compare different arrangements, or when particles interact, or when precision measurements reveal tiny shifts from what simpler theories would predict. The vacuum has consequences, but it does not behave like a hidden warehouse full of spare electricity. This brings us closer to the role of virtual particles. When physicists calculate interactions, they often represent the process using intermediate possibilities. These intermediate pieces are what we call virtual particles. They appear in the calculation when real particles interact through fields. They can be thought of as a way of organizing the influence of the field between one real event and another. But the vacuum fluctuations themselves should not be imagined as a crowd of detectable particles. The field fluctuates. The mathematics can describe aspects of these fluctuations using virtual particle language. The image is useful, but the field is the deeper story. Imagine a calm lake in early morning. From a distance, the surface looks smooth. Up close, even without wind, there may be tiny movements caused by subtle disturbances, thermal motion, small insects, or the shape of the water itself. If you tried to describe everything happening on that surface, you might break it down into waves of different sizes. Those waves are not all separate objects. They are ways the surface can move. In quantum field theory, physicists also break field behavior into modes, possible patterns of variation. The vacuum contains the minimum activity associated with those modes. This is not exactly the same as the lake, of course, because quantum fields are not water, but the comparison helps separate the field from the particle picture. We're not talking about hidden pebbles skipping across space. We're talking about the allowed patterns of fields. The phrase empty space is also misleading because space in modern physics is not merely a container. In older thinking, space could be imagined as the blank arena where matter moved. Matter was the interesting part. Space was the empty room. But 20th century physics changed that. Relativity showed that space and time are part of a dynamic structure, affected by matter and energy. Quantum theory showed that fields pervade space, and that particles are excitations of those fields. So what we casually call empty space is already layered with physical meaning. It has geometry, it has fields, it has quantum ground states, it has rules. This does not mean every patch of vacuum is secretly busy in a dramatic way. If you were drifting through intergalactic space, far from stars and planets, you would not see a shimmering storm of particles around you. Your eyes would not detect virtual photons swirling past. Your skin would not feel the vacuum fizzing. Most of these effects are not directly available to ordinary senses. They appear through careful experiments, mathematical consistency, and very precise measurements. The vacuum is not noisy in the way a crowded room is noisy. It is quiet in a way that still has measurable depth. One of the biggest misunderstandings comes from treating virtual particles as if they briefly violate the usual rules and then disappear before nature notices. You may hear it said that they borrow energy for a short time, as long as they pay it back quickly. This is a common explanation, but it can be dangerously oversimplified. Nature is not a bank manager approving tiny loans to particles with questionable paperwork. The more accurate idea is that quantum theory allows temporary intermediate states and calculations that do not look like freely travelling real particles. These states are not directly observed, and they do not have to satisfy the same conditions as real outgoing particles. The word temporary can be helpful, but only if we remember that it belongs to the calculation, not necessarily to a little object with a stopwatch. The vacuum fluctuations are likewise not moments when the universe breaks its own conservation rules. Conservation laws remain central. What changes is our understanding of what can be sharply defined and what appears as part of an intermediate description. In quantum field theory, the calculation of a real measurable process includes all possible ways the fields can contribute internally. Virtual particles are part of that internal accounting. They are not a loophole in reality. They are a feature of how quantum interactions are described. This is why two physicists might speak differently depending on the conversation. In a casual explanation, one might say that virtual particles flicker in and out of existence. In a technical discussion, the same physicist might say that this is only a metaphor and that virtual particles are internal lines in a perturbative calculation. Both statements can point toward the same territory, but they serve different purposes. The first gives the imagination something to hold. The second warns the imagination not to squeeze too hard. There is a quiet lesson here about scientific language. Many scientific terms began as metaphors or convenient labels. Spin does not mean that an electron is literally a tiny ball rotating like a planet. Colour charge in the theory of quarks has nothing to do with visible colour. Flavour in particle physics will not help you choose dessert. These words are handles, not literal descriptions. Virtual particle is similar. The word particle invites us to imagine a tiny object, but the word virtual tells us not to treat it like an ordinary particle. It is a handle for a mathematical contribution to a real process. And yet, the vacuum does seem to leave fingerprints. That is the part that keeps the subject from being just a matter of language. If the vacuum had no structure, if fields truly did nothing in their lower states, many measured effects would be different. Certain energy levels in atoms would not be shifted in the way experiments show. The strength of interactions would not vary in the same way at different distances. Very close metal plates would not experience the same tiny force. Precision particle physics would lose some of its best agreements between theory and experiment. The quiet vacuum would fail to explain the world we actually measure. The flickers are therefore not optional decorations. They are not a story added after the real physics is finished. They are connected to the way quantum fields behave. When we say beneath empty space, we should not imagine a second hidden layer under space, like a basement beneath a house. There is no little trapdoor in the vacuum leading to a storage room full of half-real particles. The beneath is conceptual. It means beneath our everyday expectation of emptiness, beneath the simple picture of space as blank, beneath the idea that nothing means no activity of any kind. A very useful way to think about it is to separate three things that often get mixed together. First, there is the quantum field, which is the basic physical entity in the theory. Second, there is the vacuum state of that field, which is its lowest energy condition. Third, there are virtual particles which appear as terms in certain ways of calculating how fields interact. When people say virtual particles flicker in empty space, they are often blending all three together. That blending can be fine for a first bedtime stroll through the idea, but eventually we need to gently untangle it. The field is real in the sense that it is part of the theory describing nature. The vacuum state is real in the sense that it has measurable consequences. The virtual particle is not real in the same direct sense as a detected particle, but it is a useful part of the description that helps us calculate the consequences of the field. Once those roles are separated, the puzzle becomes less contradictory. Unreal particles are not pushing real plates or shifting real atoms by magic. Real fields have real vacuum behaviour, and virtual particles are one way we describe the internal workings of that behaviour. This is also why the vacuum is not the same everywhere in every context. Change the environment, and the field behaviour can change. Temperature matters, boundaries matter, acceleration matters. Gravity may matter in deep ways that are still being explored. A vacuum in a simple laboratory setup is not necessarily equivalent in every practical sense to the vacuum near a black hole or in the early universe. Empty space is not one dull, identical nothing spread everywhere without character. It is shaped by the physical situation, and quantum fields respond to that situation. There is something almost comforting about this, as long as we do not let it become too mystical. The universe does not waste its quiet places. Even where there are no atoms drifting, no light passing through, no dust, no air, no warmth in the ordinary sense, the laws of physics still have content. The fields are still there. The possible patterns are still there. The conditions for interaction are still there. Empty space is not a blank page. It is more like a page that already contains the grammar of what can be written. Of course, this does not mean that every popular image is useless. The picture of flickering virtual particles can be a doorway. It tells us that the vacuum is active in a quantum way. It hints that emptiness has consequences. It suggests that reality is not limited to solid things we can directly see. For many people, that picture is the first step toward a deeper understanding. The important thing is to keep walking after we step through the doorway. If we stop there, we might think of virtual particles as tiny ghosts physically appearing in space. If we continue, we find quantum fields, vacuum states, fluctuations, and interaction terms. That view is less cartoonish, but more reliable. So when we speak of strange little flickers beneath empty space, we are really speaking about the restless ground state of quantum fields. We are speaking about the fact that a field cannot be made perfectly blank in the classical sense. We're speaking about measurable effects that arise when the vacuum is constrained, disturbed, or compared with another arrangement. We are speaking about a universe where nothing is not the same as no structure. This is the setting in which virtual particles become useful. They are not the flickers themselves in a literal object-like sense, but they are tied to our description of the processes those flickers suggest. They help us track how fields mediate forces, how particles influence one another, and how the vacuum responds when something is placed inside it. They are a language for the hidden steps between what enters an experiment and what comes out. And now the original question starts to sharpen. The issue is not whether empty space contains tiny ordinary particles that briefly sneak into existence. The issue is how quantum fields behave when no real particles are present, and why the mathematical tools used to describe that behaviour include objects we call virtual particles. To answer that properly, we have to look more closely at the word virtual itself, because in physics it does not mean imaginary in the casual sense. It means something more specific, something tied to calculation, interaction, and the difference between what can be directly detected and what can still shape the result. The word virtual can be a little misleading, because in ordinary language it often means something simulated, artificial, or almost real, but not quite. A virtual meeting is still a meeting, though usually with more people forgetting to unmute themselves. A virtual tour can show you a museum, even though your feet never touch the floor. A virtual object in a computer game can behave as if it has weight, shape, and motion, even though no one expects to find it under the desk afterward. So when we hear the phrase virtual particle, it is natural to imagine a particle that is nearly real, temporarily real, or real in some ghostly halfway sense. In physics, though, the word has a more specific meaning. A virtual particle is not a small object that briefly exists in the vacuum before vanishing. It is not a defective particle. It is not a particle that tried to become real but failed the interview. It is a feature of a calculation. More precisely, it is a way of representing the internal parts of an interaction between quantum fields. It appears when physicists use a particular mathematical method to work out how particles influence one another, scatter from one another, or produce measurable effects. It is not something that arrives in a detector. It is not something that can be isolated and examined on its own. It belongs to the unseen middle of a process, between the real things we prepare at the beginning and the real things we observe at the end. That distinction between the beginning, the middle, and the end is one of the simplest ways to understand what physicists mean. In a particle physics experiment, you might prepare real particles in a known state. You send them toward one another. Something happens, then your detectors record real particles coming out. The particles that go in and the particles that come out are the ones that can be measured as actual events. They leave tracks. They deposit energy. They trigger instruments. They behave like observable particles. The virtual particles, by contrast, are part of how the theory describes what happens during the interaction itself. They are not directly observed. They are not final products. They are internal pieces of the calculation that connects the before to the after. A simple example helps. Suppose two electrons approach each other. Electrons have electric charge, so they repel. In older classical language, we might say each electron creates an electric field, and the field pushes on the other electron. That description still works beautifully in many everyday and engineering situations. But in quantum field theory, the interaction can be described in another way. The electrons interact through the electromagnetic field, and the calculation can be organized as though a virtual photon passes between them. This virtual photon is not a little flash of light flying from one electron to the other. It is not the same as a photon from a lamp or a photon detected by a camera. It is an internal part of the quantum description of the electromagnetic interaction. This is where it is very easy to accidentally make the picture too literal. We imagine one electron tossing a photon like a tiny ball, the other electron catching it, and the two particles recoiling as if they had exchanged a microscopic tennis serve. That image can be helpful for a first glimpse, but it is not what is actually happening in a direct mechanical sense. The virtual photon is not a real photon travelling through space in a way that could be intercepted by a detector. It is a mathematical representation of how the fields connect the two electron states. The real result is that the electrons scatter. The virtual photon is part of the method used to calculate the probability of that scattering. One important difference between a real particle and a virtual one is that a real particle must satisfy the normal physical conditions that allow it to exist freely and be detected. It has a consistent relationship between its energy, its motion, and its mass. A real photon, for instance, can travel across a room and be absorbed by your eye or a sensor. A real electron can move through a detector and leave a track. These particles can be found as independent things in the incoming or outgoing parts of an experiment. A virtual particle does not have to meet those same requirements while it is inside the interaction. Physicists sometimes describe this by saying it is off-shell. That phrase comes from the geometry of the mathematics, but verbally it means that the virtual particle does not sit on the normal allowed condition for a freely observable particle. Off-shell does not mean illegal. It does not mean nature is cheating. It means the virtual particle is not being treated as a free particle. It is an intermediate contribution inside a calculation. The rules for such internal contributions are different from the rules for the particles that can appear as actual measured outcomes. If you try to promote a virtual particle into a directly observed particle, the description changes. It must become real in the proper sense, with the right physical conditions, and then it can no longer be merely the same internal object it was before. It has crossed from being part of the hidden accounting into being part of the measured result. That might sound like a technical distinction, but it matters enormously. Many popular confusions about virtual particles begin when this boundary is blurred. People hear that virtual particles exist briefly and then vanish, and they imagine little particles with tiny lifetimes. Then they ask why we cannot catch one if we measure quickly enough. But the issue is not that our instruments are too slow. It is not like trying to photograph a hummingbird in a dark room while wearing oven mitts. The issue is that a virtual particle is not the kind of thing that can be caught. It is not an event waiting to be observed. It is a piece of a computational description. There is a nice everyday comparison, though like all comparisons in quantum physics, it should be handled with care. Imagine you're planning a journey between two towns. You know where you start and where you end. There are many possible routes on the map. Some routes use highways, some use back roads, and some briefly pass through places you would never actually visit unless your navigation app had developed a mischievous personality. When you calculate travel time, you might consider many possible paths, but the possible paths in your planning are not the same as a real car travelling each one. They are ways of organising the problem. The actual journey is what happens when the car goes from start to finish. In quantum field theory, virtual particles are not exactly possible roads, but they are similar in being internal possibilities that contribute to the final predicted outcome. A better physics-based comparison is with waves. When complicated waves interact, we can break them into simpler components to understand the pattern. Those components may be extremely useful. They may let us calculate the result with precision. But not every component we use in the calculation is a separate object that exists independently. Some are parts of the representation. They help us describe the whole. Virtual particles are like that in the quantum field description. They are not detachable little things. They are the language of interaction. This becomes especially clear when we notice that virtual particles depend on how we choose to calculate. In many cases, the same physical outcome can be described without leaning on the image of virtual particles at all. Different mathematical methods can organise the same physics in different ways. The final measurable answer must agree, but the internal story may look different. This is a strong hint that virtual particles are not objects in the same straightforward sense as real particles. If they were actual little inhabitants of nature, we would expect their presence to be independent of our preferred bookkeeping method. But virtual particles are tied to a particular way of expanding and organizing the calculation. This does not make them useless or fake. Quite the opposite. A coordinate grid on a map is not part of the landscape, but it is extremely useful. Latitude and longitude lines are not painted across the Earth, yet pilots and sailors would be very unhappy without them. A virtual particle is not merely a coordinate line, but the analogy shows how something can be essential to description without being a directly existing object. Physics often works this way. We create precise languages that let us compute what nature will do. Some parts of those languages correspond directly to things we can detect. Other parts are scaffolding that supports the calculation. The scaffolding can be so effective that it feels almost real. This is why physicists continue to talk about virtual particles. They provide an intuitive and practical way to discuss complicated interactions. In quantum electrodynamics, the theory describing light and charged particles, diagrams involving virtual photons, allow physicists to organize calculations step by step. The same general idea extends to other forces. Interactions can be represented by internal exchanges. The diagrams can be read almost like little stories, with particles entering, interacting, and leaving. But the story is not a film of what literally happened. It is a compact representation of mathematical terms. The diagrams most people associate with virtual particles are called Feynman diagrams. They look simple, almost playful, like little line drawings of particles meeting and separating. Their simplicity is slightly deceptive, in the same way a recipe for pastry can look harmless, until the kitchen becomes coated in flour and regret. Each line and meeting point corresponds to a mathematical rule. The external lines represent real incoming and outgoing particles. The internal lines represent virtual particles. But the diagram is not a snapshot of tiny objects moving through space over time. It is a bookkeeping device for calculating probabilities. It helps physicists keep track of all the ways an interaction can contribute to a result. This is worth repeating in a calm way, because it is the center of the issue. A Feynman diagram is not a literal picture. It is not a photograph from the subatomic world. It is a tool. When a diagram shows a virtual photon exchange between two electrons, that does not mean a detector could be placed halfway between them and catch the photon. If you try to detect it, you would alter the process. You would be asking a different physical question, one involving real measurable particles. The virtual photon exists only as part of the internal structure of the calculation for the original interaction. The word virtual also carries another subtle meaning. It often refers to something that has the effect of something without being the thing itself. A virtual image in optics, for example, can appear behind a mirror. You can see your face in the mirror, and the image behaves as though light came from a point behind the glass, but there is no actual second person standing there, unless you live in a much more alarming house than most of us. The image is not fake in the sense of being useless. It is a real optical effect, but the apparent object is not located where it seems. In a very loose way, virtual particles have that same flavor. They are part of a real effect, but they are not real objects in the place or manner our imagination may assign to them. The danger comes when we turn a useful representation into a tiny mythology. We begin to say the vacuum is full of virtual particles, then we say those particles borrow energy, then we say they must disappear quickly. Then we imagine the vacuum as a crowded foam of little creatures trying not to get caught. It is a charming story, but the actual physics is more disciplined. The vacuum has quantum fluctuations. Fields have ground state behavior. Interactions can be calculated using virtual particles. These statements are related, but they are not identical. Keeping them separate prevents confusion. Another important point is that virtual particles are not always short-lived in the simple sense. The popular story often says they exist only for a tiny instant, but inside calculations, virtual particles can be associated with different ranges of influence depending on the situation, the force involved, and the properties of the fields. In some cases, the virtual exchange corresponds to a long-range force. In other cases, it corresponds to a very short-range effect. So the idea of a little particle surviving for a fixed tiny time can mislead us. The virtual particle is not carrying a wristwatch. It is part of an interaction whose mathematical contribution depends on the conditions of the process. The phrase borrowing energy is similarly tricky. Similarly, it comes from a loose interpretation of quantum uncertainty, but it should not be treated like an actual energy loan. Conservation of energy is not being casually suspended. The internal lines of a calculation can involve quantities that would not be allowed for real free particles, but the full physical process still respects the proper conservation laws. The incoming and outgoing measurable states balance in the ways the theory requires. Nature is not sneaking around its own rules. The calculation is summing over internal contributions that are not themselves directly observed states. This can feel strange because we're used to thinking that if something contributes to a result, it must exist as a separate cause. But quantum theory often teaches us that effects can arise from a combination of possibilities, not from one hidden classical pathway. In some experiments, a particle behaves as though multiple paths contribute to the outcome, even when we do not say the particle literally travelled each path like a tiny tourist. The final pattern is real. The calculation includes alternatives. The alternatives are not always separate little histories in the everyday sense. Virtual particles belong to this broader quantum habit. They are part of how possibilities contribute to measurable facts. There is another layer of subtlety. Some virtual particle descriptions are gauge-dependent. That means the details of the internal picture can change depending on the mathematical conventions used to describe the field, while the final observable results remain the same. This is not a flaw. It is a feature of theories with certain symmetries. But it is another reason physicists are cautious about saying virtual particles are real objects. If the internal details can shift with the description, while the measurable answer stays fixed, then the measurable answer is what we should treat as physically solid. The virtual particles are useful elements within a chosen description, not independent items we can list in an inventory of the universe. This does not mean the entire idea should be thrown away. Far from it. The language of virtual particles is one of the most successful and practical tools in modern physics. It lets physicists calculate how electrons scatter, how atoms shift their energy levels, how particles decay, how forces behave at different distances, and how subtle corrections appear in precision measurements. It provides a way to organize what would otherwise be an overwhelming set of field interactions. The fact that virtual particles are not directly real does not make them weak, it makes them technical. And technical things can be extremely powerful even when they are not easy to picture. Think of the pressure inside a gas. We say gas pressure comes from molecules bouncing off the walls of a container. That picture is fairly literal, because molecules are real objects and collisions really occur. But we also speak of centre of mass, electric potential, temperature, and other quantities that are not objects you can pick up. These quantities are real in a different way. They describe patterns, relationships, and measurable properties. Virtual particles are further from direct experience than temperature or pressure, but the same lesson applies. Not everything important in physics is a little object. Some important things are parts of a description that allow us to predict what little objects, fields, and instruments will do. There is also a practical reason for the word particle. Quantum field theory often begins with fields, but when those fields are excited in stable, detectable ways, we observe particles. Since the same field can appear in a real external form or a virtual internal form, the particle language carries over. A photon can be real when it is emitted and absorbed as light. A photon can be virtual when it appears as an internal mediator of an electromagnetic interaction. The word photon is used in both contexts because the same electromagnetic field is involved, but the status is different. One is an observable excitation, the other is an internal contribution. Same field, different role. This is similar to an actor appearing on stage versus a character mentioned in a script note. The actor on stage is part of the performance the audience sees. The script note shapes what happens, but it is not itself a performer standing under the lights. That comparison is not perfect, but it helps. Real particles are on stage, in the sense that they can be detected as incoming or outgoing events. Virtual particles are backstage instructions in the calculation. They influence the structure of the performance, but you do not find them bowing at the end. The phrase change reality should therefore be understood carefully. Virtual particles do not change reality as independent hidden objects. They do not sneak into the world, shove something, and vanish. Instead, the theory that includes virtual particles describes how fields interact, and those interactions produce real measurable changes. The virtual particles are part of the description of the field behavior. Reality is changed by the underlying fields and their interactions. Virtual particles are how one powerful method talks about those changes. This helps explain why scientists can say virtual particles are not real and still take them seriously. They are not real as free particles. They are not unreal as meaningless inventions. They occupy a middle category that is common in advanced physics, but uncomfortable in ordinary speech. They are calculational entities with physical relevance. They are not directly observed, yet they belong to a framework whose predictions are tested with extraordinary precision. They are not little things in space, yet they help describe how things in space behave. A careful listener might ask whether this is just a fancy way of saying we do not know what is really happening. There is some humility required here. Quantum field theory gives us an astonishingly successful way to predict observations. But the mental picture behind the mathematics is not always unique. Physicists often know very precisely what can be measured and how to calculate it, while remaining cautious about which parts of the calculation should be treated as literal reality. That is not a weakness of science. It is part of its honesty. Science does not need every useful concept to be a miniature object. It needs concepts that connect clearly to evidence. So when physicists say virtual, they are usually telling us several things at once. They mean the particle is internal to the calculation. They mean it is not directly detectable as a free particle. They mean it need not satisfy the same conditions as a real particle. They mean it represents a contribution from a quantum field interaction. They mean it is useful, but should not be overpictured. All of that is packed into one small word, which is a lot of responsibility for 8 letters. This is why the topic can feel slippery. The phrase virtual particle invites imagination, then immediately demands restraint. It gives us a picture and then asks us not to believe the picture too literally. But maybe that is not so unusual. Much of physics works by building models that are good enough to guide us, then refining them when they begin to mislead. We first learn that light is a ray, then a wave, then a particle, then an excitation of a quantum field, and at each step the old picture remains useful in the right setting but incomplete outside it. Virtual particles are another case where the picture is useful if we remember what it is for, and with that the question becomes less about whether virtual particles are real in a yes or no sense, and more about how a non-observable internal feature of a theory can be connected to observable physical effects. That connection runs through quantum fields, interactions, and the way uncertainty shapes what can be said about intermediate states. It also leads into one of the most common stories told about virtual particles, the idea that they borrow energy for a very short time. That story is memorable, but it needs some careful unpacking, because the universe is not quite doing shady accounting in the dark. It is following quantum rules that are stranger, more precise, and far more interesting than a simple loan from nowhere. One of the most common stories about virtual particles begins with a phrase that sounds as if the universe has a very relaxed attitude toward bookkeeping. You may have heard that virtual particles borrow energy from empty space, appear for a tiny moment, and then disappear again before nature notices. It is a memorable image. It makes the vacuum feel like a busy little marketplace where particles take out impossibly short loans, buy a moment of existence, and then pay everything back before the cosmic accountant has time to raise an eyebrow. It is also one of those explanations that is useful only for a few steps before it starts quietly leading us into the bushes. The phrase borrowed energy is not completely meaningless, or it would not have survived in popular explanations for so long. It points toward a real feature of quantum theory, which is that the intermediate parts of a process do not always behave like ordinary observable particles. It also points toward the deep connection between energy, time, and uncertainty. But if we take the phrase too literally, we end up imagining virtual particles as tiny rule breakers sneaking around the universe with a stopwatch and a guilty expression. That is not what physicists mean. Nature is strange, certainly, but it is not sloppy. Energy conservation is not a suggestion that quantum physics occasionally ignores because the paperwork is inconvenient. To see what is really going on, it helps to begin with uncertainty itself. In everyday life, uncertainty usually means we do not know something. If you are uncertain whether there is one biscuit left in the tin, the biscuit situation is still definite. Either the biscuit is there or it is not. Your uncertainty is a limitation in your knowledge, not necessarily in the biscuit, though if the biscuit has been in a household with several people, its exact status may indeed be a matter of urgent investigation. Quantum uncertainty is different. It is not just a statement about human ignorance. It is built into the way physical systems behave. Some properties cannot be made perfectly definite together. The more precisely one is pinned down, the less precisely another related property can be specified. This is not because our measuring tools are clumsy, although they often are in daily life. It is because quantum objects are not little classical objects carrying perfectly sharp values around with them at all times. The theory does not allow certain pairs of quantities to be simultaneously exact in the way ordinary intuition expects. The most famous version involves position and motion, but energy and time have their own relationship too. This relationship is often described by saying that if a process happens over a very short time, its energy can be uncertain by a larger amount. If you try to define the energy of something during only a brief interval, the energy cannot be assigned with perfect sharpness. That is the seed from which the borrowed energy story grows. The popular version says that if the time is short enough, energy can be borrowed briefly, allowing virtual particles to appear as long as the debt is repaid quickly. The trouble is that time is not exactly the same kind of quantity in ordinary quantum mechanics as position. Time is usually treated as the parameter that labels change, not as an observable property of a particle in quite the same way. So the energy-time uncertainty idea must be handled more carefully than the simpler popular slogan suggests. It does not mean the universe permits energy conservation to be violated for a tiny moment. It means that the energy associated with very short-lived or intermediate processes is not sharply defined in the same way as the energy of a stable, freely observed particle. That distinction may sound small, but it is the difference between disciplined physics and a fairy tale with lab coats. Imagine listening to a musical note. If someone plays a long, steady note on a violin, you can identify its pitch very accurately. The note lasts long enough for your ear and brain to settle into it. But if the sound is just a tiny click, a brief tap, it does not have a single clean pitch in the same sense. It contains a spread of possible frequencies. The shorter the sound, the less sharply defined the pitch. No rule has been broken. Nothing has borrowed sound from the future. It is simply a feature of waves. Duration and sharpness of frequency are linked. This analogy is helpful because quantum particles and fields have wave-like behavior. Energy is related to how the quantum state changes with time. If a state persists in a clean, stable way, its energy can be sharply defined. If we are dealing with a fleeting intermediate disturbance inside an interaction, the energy associated with that internal contribution may not have the same sharp, definite status. That does not mean energy conservation has failed. It means we're not talking about a free observable particle with a clean measurable energy. We're talking about a temporary internal feature of a calculation. This is where virtual particles enter the story again. A real particle, one that can travel freely and be detected, must satisfy the usual physical requirements for its energy, motion, and mass. It has to be a possible observed state. A virtual particle inside an interaction does not have to satisfy those same conditions. It can carry quantities through the calculation in a way that would not correspond to a free particle arriving in a detector. Physicists sometimes say it is off-shell, but in plain words, it is not on the normal track required for real observable particles. It is an internal piece of the mathematical process, not an independent traveller. The borrowed energy story is an attempt to explain this internal freedom. It says, in effect, that because the virtual particle exists only briefly, it can have an energy that would not be allowed for a real particle. But that wording can make it sound as though the particle genuinely exists for a brief physical time and nature politely looks away. The more careful version is that when calculating an interaction, quantum theory includes intermediate contributions that are not themselves directly observable states. These contributions can involve quantities that differ from what a free real particle would have. The full process, from what enters to what leaves, still obeys the conservation rules. The beginning and ending accounts balance. The middle is not a hidden crime scene, it is a mathematical summation over allowed internal contributions. A household comparison may help as long as we do not lean on it too hard. Suppose you are balancing your monthly budget. At the beginning of the month you know your starting amount. At the end you know where the money went. In between you might use categories, estimates, transfers, pending payments, and temporary labels to make sense of the flow. Some entries in your planning spreadsheet are not physical coins sitting in a jar. They are accounting devices that help connect the initial and final totals. If someone looked only at one line in the middle, they might misunderstand what it means, but the entire account can still be perfectly consistent. Virtual particles are not budget categories exactly, but the comparison shows why an internal bookkeeping element should not automatically be treated as a separate object. The cosmic accounting trick, then, is not that energy conservation is broken. It is that quantum calculations are allowed to use internal terms that do not look like real particles. The final answer only concerns observable outcomes. Those outcomes must respect the rules. The virtual particle is part of how the theory gets from the prepared state to the measured state. It carries information through the calculation, not like a tiny courier running across space, but like a term in the structure of an interaction. This is especially important because the word energy feels very concrete to us. We think of energy as something stored, spent, used, drained, or delivered. A battery has energy. Food has energy. A tired person claims to have no energy, which may not satisfy a physicist as a formal measurement, but is emotionally convincing after a long day. So when people hear that the vacuum lends energy, they imagine a supply. They imagine empty space as a bank. But in quantum field theory, the situation is more subtle. Energy is a property of states and interactions. The vacuum has a ground state. Fields fluctuate. Intermediate contributions and calculations may not correspond to free states. This is not the same as a reservoir casually handing out energy coupons. There is a reason the misleading story feels attractive. It gives the mind something mechanical to picture. A particle pair appears. One particle goes one way, the other goes another. They annihilate. The debt is paid. The vacuum returns to normal. It sounds tidy. It sounds visual. It also sounds more definite than quantum theory often allows. In reality, before a measurement, quantum processes are described through amplitudes and probabilities. The theory adds together contributions from different possible internal arrangements. A virtual particle is one of those internal elements in a particular representation. It is not necessarily something that happened as a little scene in miniature. That last point is worth sitting with for a moment. In everyday life, when an event happens, we assume there is a single hidden story behind it. If a cup falls off a table, maybe a cat nudged it. Maybe your sleeve caught it. Maybe the table was tilted. There is one actual sequence of events, even if you do not know it. Quantum physics often resists that simple picture. To calculate what we observe, we may need to include many possible contributions, and the final outcome can depend on how those contributions combine. The calculation is not always a record of one secret classical history. It is a way of getting the probabilities for what will be measured. So when a diagram shows a virtual particle exchange between two real particles, we should not treat the diagram as a hidden camera view of the event. It is more like a compact instruction for one contribution to the probability. The virtual particle in that diagram is not caught halfway, because there is nothing to catch in that sense. It is internal to the calculation. Asking where it was exactly, or how long it existed exactly, can be like asking where the melody is located inside a written sheet of music before anyone plays it. The question borrows the wrong kind of reality. Still, the result of the calculation is not vague at all. It can predict how likely particles are to scatter at certain angles. It can predict tiny corrections to magnetic properties. It can predict shifts in atomic energy levels. It can predict the behavior of forces at different distances. These predictions are tested against experiments. The agreement can be extremely precise. This is why the language of virtual particles remains so valuable. It may be dangerous as a literal picture, but it is powerful as a calculation tool. The uncertainty idea also helps us understand why virtual effects often become important at very small scales. When you probe a system more closely, or look at interactions over shorter distances and times, the influence of quantum fluctuations and intermediate contributions becomes harder to ignore. The simple classical picture begins to lose its grip. The vacuum is no longer just a quiet background. It participates through the fields, corrections appear. The measured behavior differs slightly from what a less complete theory would predict. Those differences are often tiny, but physics is very good at noticing tiny differences. It is one of the universe's less relaxing hobbies. Take the electron, for example. It has a magnetic behavior that can be measured with extraordinary precision. A simple theory gives a first answer. Quantum field theory then adds corrections, many of which are described using virtual particles. The electron interacts with its own electromagnetic field. Virtual photons appear in the calculations. Other virtual effects contribute too, depending on the level of precision. The final predicted value matches experiment with remarkable accuracy. No one is catching a virtual photon orbiting the electron like a moth around a lamp. Instead, the field interactions alter the measurable magnetic property, and virtual particle diagrams organize the corrections. This shows why the phrase change reality needs care. The virtual particles do not change the electron as little physical objects buzzing around it. The quantum fields and their interactions determine the electron's measured properties. Virtual particles are one way of representing those interactions in the calculation. The change is real because the measurement changes. The virtual particle is not real in the same way because it is not an observed particle. It is the path the mathematics takes through the forest, not necessarily a creature living among the trees. The same caution applies to particle pairs said to appear from the vacuum. In some physical situations, strong fields or curved space-time can lead to the creation of real particles. That is different from ordinary virtual particles in empty space. Real particle creation means detectors could, in principle, record actual outgoing particles. Virtual contributions are internal. The distinction matters because popular explanations often blur them together. They say particles appear from nothing, and suddenly the listener is left with the impression that empty space constantly manufactures matter as a hobby. Quantum theory is stranger and more disciplined than that. Real particles require the right physical conditions and energy flow. Virtual particles inside calculations are not the same thing. A useful phrase is that virtual particles are allowed in the middle, not the edges. The The edges of a process are what we prepare and what we observe. Those must be physically real states. The middle is where the mathematical description includes internal possibilities. The middle can contain virtual contributions that do not correspond to free particles. But when everything is added up, the final observable result is consistent and conserved. The cosmic accounting works. It is just not the kind of accounting where every internal line is a separate coin. This also explains why virtual particles cannot be used to build a perpetual motion machine or extract endless energy from the vacuum. If virtual particles were really borrowing energy in the crude sense, one might wonder whether clever engineers could catch them before they pay it back, perhaps place a tiny net in the vacuum and harvest the flickers. But because virtual particles are not freely existing little objects, there is nothing like that to harvest. The measurable vacuum effects depend on changes in conditions, boundaries, fields, or interactions. You cannot simply grab virtual particles out of nothing. The universe is peculiar, but it is not that easily tricked. The Casimir effect, which comes next in our journey, is often described in exactly this tempting language. Two plates are placed close together. Virtual particles outside the plates outnumber those between the plates. The outside pressure pushes the plates inward. This picture can be useful as a first sketch, but it is not the full explanation. The deeper version involves how the plates alter the allowed patterns of quantum fields between them compared with outside them. The force arises from a difference in vacuum energy conditions. It is a real effect, but not because tiny temporary particles are literally hammering the plates from the outside like a swarm of invisible hailstones. The reason we are taking time with this is not to drain the wonder from the subject. It is to protect the wonder from becoming a cartoon. The true quantum picture is not less strange than the borrowed energy story. It is more strange, but also more reliable. It tells us that reality is not made only of definite objects carrying definite properties through definite pathways. It tells us that fields, uncertainty, intermediate states, and probability amplitudes all matter. It tells us that what happens between preparation and observation cannot always be reduced to a familiar little movie, and yet from this unfamiliar machinery, precise measurable facts emerge. There is something deeply satisfying about that. The universe keeps its accounts, but the ledger is not written in the language of common sense. The totals balance, but the intermediate steps are quantum steps. The vacuum is not a blank nothing, but it is not a chaotic bank of free energy either. Virtual particles are not real particles, but they are not meaningless. Energy is conserved, but the way energy is assigned inside a short-lived intermediate process is not the same as the way energy is assigned to a particle we can observe. So perhaps the borrowed energy story should be retired gently, not thrown away with a scolding lecture, but folded up and placed on the shelf marked useful first metaphors. It helped many people glimpse that the vacuum is active and that quantum theory allows strange intermediate behaviour. But now we can replace it with a better picture. A virtual particle is an internal contribution in a quantum field interaction. Because it is not a free observable particle, it need not have the same sharply defined properties as one. The uncertainty associated with time and energy helps explain why short processes do not have the same clean energy assignment as stable states. The full physical process still obeys conservation laws. Nothing is being stolen from the universe. Nothing is being smuggled past reality. And this careful understanding prepares us for one of the most famous cases where the vacuum seems to do something almost tangible. Two uncharged plates placed extremely close together in empty space can feel a tiny attraction. No ordinary particles need to be blowing between them. No visible force is pulling them. Yet the plates move as though emptiness itself has developed a preference. To make sense of that, we have to take the idea of vacuum fluctuations out of the realm of metaphor and place it beside a real experiment, one where nothing under the right conditions can gently push. Now that the borrowed energy story has been set down gently and treated with the caution it deserves, we can walk into one of the most famous places where the quantum vacuum seems to reach out, and touch the ordinary world. It is a beautifully simple experiment in its basic idea, almost suspiciously simple, the kind of setup that makes you wonder whether nature is hiding something enormous in plain sight. Take 2 uncharged metal plates, place them extremely close together in a vacuum, remove the air, remove any obvious source of pressure, make sure the plates are not electrically charged, then watch carefully. If the plates are close enough and the experiment is clean enough, they attract one another. At first, that sounds like a trick. Plates do not simply decide to move together because they are lonely. If 2 magnets attract, we know what to blame. If 2 charged objects pull or push, we know electric forces are involved. If something falls, gravity has entered the conversation, as it often does, with no regard for whether anyone invited it. But in the Casimir effect, the plates are neutral. The surrounding space is empty in the practical laboratory sense, and still a tiny force appears. It is not a large force. It will not slam dinner plates together across the kitchen, which is probably for the best. But it is real, measurable, and deeply revealing. The effect is named after the Dutch physicist Hendrik Casimir, who predicted it in the middle of the 20th century. He was thinking about quantum fields and the strange fact that empty space is not simply blank. If the vacuum has fluctuations, and if metal surfaces can affect which field patterns are allowed nearby, then putting 2 plates close together should change the vacuum conditions between them, compared with the vacuum outside them. That difference should show up as a force. The prediction was tiny, but not impossible to test. Later experiments confirmed that the force exists. Empty space, under carefully arranged conditions, behaves as if it can push. This is where popular explanations often bring back the virtual particle picture. The usual story goes like this. Empty space is full of virtual particles popping in and out of existence. Between the plates, only certain virtual particles can fit, while outside the plates there is more room for all kinds of virtual particles. So there are more virtual particles outside pushing inward than inside pushing outward, and the plates are pressed together. It is a wonderfully visual story. You can almost picture the plates being squeezed by invisible quantum popcorn. It is also not the careful explanation physicists rely on when they do the real work. The better way to think about it begins with fields. Quantum fields can have different modes, meaning different possible patterns of vibrational variation. Even in the vacuum state, those modes contribute to the field's ground state behavior. The metal plates impose boundaries. They restrict what kinds of electromagnetic field patterns can exist between them. Not every possible pattern fits. The situation is a little like a guitar string fixed at both ends. It cannot vibrate just any way at all. Only certain standing wave patterns are allowed. The string's length determines the allowed notes. Change the length, and you change the possible vibrations. Between the Casimir plates, the electromagnetic field is similarly constrained, though in a more subtle quantum way. The plates act like boundaries for the field. The field outside the plates is less restricted. The result is a difference between the vacuum energy associated with the allowed field modes inside the gap and the vacuum energy outside. The plates feel a force because changing their separation changes that difference. Nature tends to move the arrangement in the direction that lowers the relevant energy. The attraction is not caused by little pellets physically striking the plates from outside. It arises because the boundary conditions reshape the vacuum field itself. That phrase boundary conditions may sound dry enough to put even a very alert person into a thoughtful doze, but the idea is simple. A boundary condition tells a system what it must do at an edge. If you hold a rope at one end and shake it, the way waves travel depends on whether the other end is fixed, loose, or tied to a very patient friend. If sound moves through a room, the shape of the walls affects echoes. If light reflects inside a cavity, the surfaces determine which patterns can persist. Boundaries matter. They do not merely sit there. They define what the fields and waves can do. The Casimir effect is the quantum vacuum taking boundaries seriously. The plates do not need to be charged in the ordinary way. They do not need to send signals to each other. They simply restrict the electromagnetic field modes in the region between them. Because the quantum vacuum is not an absence but a ground state with structure, altering the allowed modes alters the physical situation. When the plates are very close, the difference becomes large enough, though still tiny, to measure. It is worth pausing on how strange this is. In classical physics, if there is no radiation, no particles, no air and no electric charge, we would not expect the space between neutral plates to matter much. The plates might attract weakly through gravity, but that would be absurdly small for laboratory plates. They might have tiny residual charges or surface imperfections, and experimenters have to work hard to account for those. But after those ordinary effects are controlled, quantum theory says there should still be a force, not because something material fills the gap in the usual sense, but because the vacuum fields are altered by the geometry. Geometry is doing real work here. The distance between the plates matters. Bring them closer, and the set of allowed field patterns between them changes. The force becomes stronger as the gap shrinks. Pull them apart, and the effect rapidly weakens. This is why the Casimir effect is most relevant at very small distances, often in the range where microscopic machines and nanotechnology begin to operate. At the scale of everyday objects, the force is usually too small to notice. At extremely tiny separations, it can become significant, sometimes even troublesome. Engineers working with small mechanical systems may have to consider it, because parts that are very close together can attract and stick. Nothing is rarely a problem when your machinery is large. Nothing becomes much more opinionated when your machinery is tiny. The first time one hears this, it can feel as if the vacuum has become a substance pressing on objects. That picture is tempting. It is also not entirely useless, if used carefully. Pressure is a familiar way to think about forces from many small contributions. Air pressure pushes equally from all sides in ordinary life. If there is less pressure on one side, an object moves. The virtual particle explanation borrows that intuition. It says the outside has more vacuum activity than the inside, so the plates are pushed together. But the true calculation is not counting little particles bouncing around. It is comparing the allowed modes and the associated vacuum energies in different regions. The pressure image is a translation for human imagination, not a literal microscopic movie. A good analogy is the sound inside a room. Suppose you stand in a small bathroom and hum a note. Some notes seem to resonate more strongly than others because the room supports certain sound patterns better than others. Change the room's size or shape, and the resonances change. No one would say that tiny sound particles are trapped or excluded in the literal sense. We would say the room allows certain wave patterns. With the Casimir effect, the electromagnetic field in the vacuum has allowed patterns, and the plates change them. The difference is that even when no real light is present, the quantum field still has ground state fluctuations associated with its possible patterns. The room is silent, but its ability to resonate still matters. There's another way to feel the idea. Imagine an ocean harbour with walls. Waves outside the harbour can have many different forms. Inside a narrow channel, only some waves fit well. The water's behaviour is shaped by the walls. If the waves exert forces on the walls, then changing which waves are allowed changes the forces. The Casimir effect is not literally water waves, and the vacuum is not a liquid sloshing around between metal plates. But the comparison captures the role of restrictions. The boundaries limit the patterns, and the resulting difference has consequences. This helps explain why saying nothing pushes the plates together is both true and not quite true. There is no ordinary substance doing the pushing. There is no wind. There is no stream of real particles flying inward. In that sense, nothing pushes, but the nothing in question is the quantum vacuum, and the quantum vacuum is not a featureless absence. It is the lowest energy state of fields, and that state depends on the conditions placed upon the fields. So the more careful statement is that the plates are attracted because the presence of boundaries changes the vacuum field modes, producing a measurable force. It is a little less catchy, but far less likely to cause trouble at a dinner party, unless your dinner parties are extremely specialised. Experiments measuring the Casimir effect are delicate. The plates or surfaces must be very close, often much closer than the width of a human hair. They must be clean and carefully controlled. Real metals are not perfect ideal boundaries. Temperature can matter. Surface roughness can matter. Tiny leftover electric patches on the surfaces can imitate or obscure the effect. Measuring the Casimir force is therefore not as simple as placing 2 sheets of foil in a jar and waiting for quantum magic. It requires precision, patience, and a remarkable tolerance for things that go wrong at tiny scales. Experimental physics is often less like waving a wand and more like persuading reality to stop fidgeting long enough to answer a question. What makes the effect so important is not merely that the plates move. Many things move. Cats move at 3 a.m. for reasons still unknown to science. The importance is that the movement connects directly to the reality of quantum vacuum behavior. It demonstrates that vacuum fluctuations are not just philosophical decorations or mathematical excess. Under the right conditions, changes in the vacuum state can produce forces. The effect is small, but small is not the same as imaginary. A tiny force measured carefully can carry an enormous message. This is why the Casimir effect often appears in discussions of whether virtual particles are real. It seems to offer a clean example of virtual particles causing something physical. But now we can say it more carefully. The Casimir force is real. It can be measured. The virtual particle story is one way to picture why the vacuum can exert an effect. But the most accurate explanation does not require imagining virtual particles as little objects colliding with the plates. It relies on quantum fields, boundary conditions, and changes in vacuum energy. Virtual particles are useful when calculating or interpreting aspects of the field behavior, but the effect itself is not proof that virtual particles are real in the same sense as detected particles. That distinction is subtle, and it is exactly where the topic becomes interesting. If a model involving virtual particles helps predict the Casimir effect, does that make virtual particles real? Some would say no, because the same effect can be derived in ways that do not treat virtual particles as literal objects. What is real is the field, the boundary, the measurable force. The virtual particles are part of a representation. Others might say that if a concept appears in a successful description and consistently accounts for real effects, it has a kind of physical reality, even if not the simple object like reality of a marble or an electron in a detector. The debate often depends on what one expects the word real to mean. For our purposes, the safest view is also the clearest. The Casimir effect does not show that virtual particles are little temporary things physically pressing the plates together. It shows that the quantum vacuum has structure, and that changing the allowed field modes changes measurable forces. Virtual particle language can help us talk about this, but it should not be mistaken for a photograph of what is happening. The universe is not obligated to match our favourite cartoon. The effect also reminds us that the vacuum is not independent of matter. The plates and the vacuum are not separate in the way everyday intuition might suggest. The plates are made of charged particles. Those charged particles interact with the electromagnetic field. Because of those interactions, the plates impose conditions on the field. The field's ground state adjusts to those conditions. Then the adjusted field conditions produce a force on the plates. This is a loop of mutual influence. Matter shapes fields. Fields affect matter. The vacuum is not a stage that remains untouched while objects perform upon it. It is part of the performance. This point is easy to miss because metal plates look so solid and ordinary. But a metal surface is not merely a hard boundary in the human sense. Inside the metal, electrons are mobile. Electromagnetic fields interact strongly with those electrons. That is why metals reflect light. That is also why idealized metal plates can be treated as boundaries for the electromagnetic field in the Casimir setup. The plates tell the field, in effect, which patterns are allowed at the surface. Of course, the plates do not literally speak. If metal plates start speaking, you have discovered either new physics or you need more sleep. But through their physical properties, they constrain the field. The closer the plates are, the more restrictive the space between them becomes for certain field modes. Some long wavelength patterns cannot fit in the gap. Outside, those patterns are still available. This difference is not a simple matter of more particles outside than inside, but it does create an imbalance in the vacuum's contribution to the energy and pressure. The plates are drawn together. The force is a statement about the difference between two arrangements of the same underlying fields. One of the satisfying things about the Casimir effect is that it turns an abstract idea into something mechanical. Vacuum fluctuations can sound like a cloudy phrase. Boundary conditions can sound like a phrase that should be filed in a drawer and forgotten until exams. But two plates attracting in a vacuum is concrete. It is a physical event. It lets us say, with appropriate caution, that the quantum vacuum is not just an idea. It has consequences that can be measured with instruments. There is a small philosophical lesson here too. We often think reality must be made of things, particles, objects, bodies, stuff. But the Casimir effect is more about arrangements than things. It is about what patterns are allowed and what patterns are excluded. It is about the difference between one configuration and another. The force does not come from adding a new visible substance between the plates. It comes from changing the conditions under which the field exists. Reality is not only objects, it is also relationships, constraints, and permitted possibilities. This is very quantum. In a classical world, if nothing is present, nothing should happen. In a quantum field world, what can happen depends on the state of the fields, and the state of the fields depends on the whole physical setup. The vacuum near boundaries is not identical to the vacuum far from boundaries. The absence of particles does not mean the absence of influence. A quiet field still has a structure, and if that structure changes with distance, shape, or material, real forces can appear. It is also important not to overstate the effect. The Casimir effect is not evidence that thoughts shape the vacuum, or that empty space can be tapped for endless power, or that reality is secretly made of wishful thinking and silver plates. Physics has a way of attracting extravagant claims when its real results are already wonderful enough. The Casimir effect is specific. It involves quantum fields and boundary conditions. It is measurable under controlled circumstances. It does not mean that empty space will push any two objects together in any situation, nor does it give us a simple machine for extracting unlimited energy from nothing. The vacuum has rules. It is strange but not gullible, but not. In fact, the precision of the Casimir effect depends on taking the rules seriously. Real experiments must account for temperature, material properties, geometry, and electromagnetic effects. The simplest picture of two perfect parallel plates is an idealization, useful for understanding the core idea. Actual measurements often use a sphere and a plate because keeping two plates perfectly parallel at tiny separations is extremely difficult. Nature does not hand out clean textbook diagrams in the laboratory. It gives surfaces with roughness, stray charges, vibrations, and dust, which is the traditional enemy of anyone trying to measure small things. Yet despite all this, the effect has been observed and studied. It has become part of the broader evidence that vacuum fluctuations and quantum field behavior are physically meaningful. It is not alone. Other effects, such as tiny shifts in atomic energy levels and corrections to particle properties, also point toward the same underlying lesson. The vacuum is not empty in the classical sense. It is the ground state of fields, and those fields have consequences even when no real particles are present. This returns us to the central question in a more mature form. If virtual particles are not real, why do they change reality? In the Casimir effect, we see that it may be better not to say virtual particles change reality. Instead, the quantum fields change reality. The vacuum state of those fields changes when boundaries are introduced. Virtual particles are one way to describe or calculate aspects of that change. If we mistake the description for little objects, we become confused. If we treat the description as a tool pointing toward field behavior, the puzzle becomes clearer. There is an elegance in this. The plates do not need an invisible wind. They do not need hidden matter. They do not need magic. They simply sit close together, and by doing so, they alter which field patterns can exist between them. The vacuum responds. The response has energy. The energy depends on the distance. A force follows. No formula is needed to appreciate the meaning. Two ordinary pieces of material can reveal that empty space has a quantum texture. That texture is not something our senses evolved to notice. Human beings are very good at detecting falling rocks, changing weather, facial expressions, and whether a cup of tea has gone cold. We are not naturally good at noticing shifts in vacuum energy between metal surfaces separated by microscopic distances. For that, we need theory, instruments, and a willingness to trust results that do not resemble everyday intuition. The Casimir effect rewards that willingness. It whispers that the universe remains active even where we thought there was only absence. And once we accept that, the idea of forces begins to look different too. Perhaps forces are not always best imagined as invisible hands pushing across space. In quantum field theory, forces arise from fields and interactions. Virtual particles often appear as the mediators in our calculations. They help us organize how one particle influences another. The Casimir effect is a special case where the vacuum itself, shaped by boundaries, produces a force between larger objects. But the same broader language of fields and virtual exchanges also helps explain the familiar forces between particles, including the electromagnetic repulsion that keeps atoms structured and stops your hand from passing through a table, which most tables appreciate. From here, the question naturally widens from two plates in a vacuum to the forces that build the material world, because virtual particles are not only invoked when nothing pushes, they also appear when everything pushes, pulls, scatters, binds, and holds together. To see why virtual particles matter so much, we need to move from empty space between metal plates to something more familiar, though perhaps not more obvious. We need to talk about forces, not the dramatic kind where someone in a film raises a hand and furniture flies across the room, although physicists would certainly have questions about the energy budget. I mean the ordinary forces that make the world hold together, the ones so constant and dependable that we forget they need explaining at all. The push between two magnets, the pull of an atomic nucleus on an electron, the resistance you feel when your hand rests on a table, the reason atoms do not simply collapse inward, and the reason matter does not pass through matter like mist. In everyday life, force feels like contact. A hand pushes a door, a foot presses the floor, a spoon stirs tea, something touches something else, and the motion changes. That kind of force makes intuitive sense because the cause is right there in front of us, usually leaving fingerprints. But many of the most important forces in nature do not look like contact at first. The Earth pulls the moon without a rope. A magnet pulls a paper clip across empty space. Two electric charges repel each other even when they are not touching. For a long time, this action at a distance felt deeply mysterious. How can one thing influence another across a gap? What crosses the space between them? What carries the message that says move this way, not that way? Classical physics answered this with fields. A charged particle creates an electric field around it. Another charged particle placed in that field feels a force. A magnet creates a magnetic field. A compass needle responds. The field is the thing spread through space that carries the influence. This was already a major shift in thinking. Instead of one object magically tugging another from afar, the first object changes the condition of the space around it, and the second responds to that changed condition. The space between things is no longer irrelevant. It has physical content. Quantum field theory keeps the field idea but changes its character. Fields are not just smooth, invisible conditions spread through space. They are quantum fields, and their excitations appear as particles. Light is an excitation of the electromagnetic field. Electrons are excitations of the electron field. Other particles arise from their own fields. Forces in this picture are not simply pushes delivered by invisible classical fields, they are interactions among quantum fields. When particles influence one another, the theory describes the process through the exchange of field disturbances. In many calculations, those disturbances appear as virtual particles. The most familiar example is the electromagnetic force. This is the force between electrically charged particles. It is responsible for light, chemistry, electricity, magnetism, and the fact that your chair does not politely allow you to sink through it. In quantum electrodynamics, the quantum theory of the electromagnetic force, charged particles interact by exchanging photons. Real photons are particles of light. They can travel freely, be emitted by a lamp, absorbed by your eye, or detected by instruments. Virtual photons are different. They are internal parts of the calculation that describe the electromagnetic interaction between charged particles. Suppose two electrons approach one another. Because both have the same kind of electric charge, they repel. In a simple picture, one electron emits a virtual photon and the other absorbs it. The exchange changes the motion of both electrons. That picture is easy to hold in the mind, and it is not useless. It tells us that the force is mediated through the electromagnetic field. But it should not be imagined as one electron throwing a tiny glowing ball at the other. A virtual photon is not a little spark of light moving between them in a way that could be intercepted. It is not a real photon with a secret mission. It is a mathematical representation of how the electromagnetic field carries the interaction. The effect, however, is real. The electrons scatter, their paths change. Detectors can measure the outcome. The calculation using virtual photons predicts the probabilities of different outcomes with extraordinary precision. That is why virtual particles are taken seriously. They are not real particles in the detector sense, but they are part of a theory that tells us exactly how real particles behave. The virtual photon is like a term in the conversation between fields. You do not hear it separately as a spoken word, but without that internal structure, the conversation would not come out correctly. This is already enough to soften the puzzle. Virtual particles help shape real forces because forces themselves, at the quantum level, are not little hands reaching across space. They are interactions in fields. Virtual particles are the way one powerful method describes those interactions. They mediate in the calculation. They connect the incoming particles to the outgoing particles. They help encode how energy and momentum are transferred between real objects, while not being real objects themselves. A common source of confusion is the phrase force carrier. Physicists often say photons carry the electromagnetic force, gluons carry the strong force, and weak bosons carry the weak force. This language is useful, but it can sound more literal than intended. For real particles, a force carrier can be observed under the right conditions. A real photon from a lamp is certainly real. A real gluon cannot be isolated freely in the same way because of the special behavior of the strong force. But gluons are still part of the particle content of the theory. In force calculations, though, the carriers are often virtual. They appear inside the interaction. They are the internal lines of the process, not objects flying around waiting to be caught. Think of two ice skaters facing each other. If one throws a heavy ball to the other, both skaters move because momentum is exchanged. This is often used as an analogy for repulsive forces. One particle throws something and the other recoils. But the analogy has limits. It works only as a rough image. Quantum exchange is not necessarily a literal throwing of a ball. Also, it becomes awkward when trying to explain attraction. If two particles attract, did one throw a ball in such a clever way that the other moved closer? The mental picture starts doing acrobatics, and not graceful ones. The field calculation is more reliable. Virtual exchange changes the combined state of the particles, and the resulting force can be attractive or repulsive depending on the interaction. The electromagnetic force can attract or repel. Opposite charges attract like charges repel. In the virtual photon language, both cases involve electromagnetic interaction, but the mathematical details produce different signs of the effect. We do not need formulas to understand the basic point. The same field can mediate different outcomes depending on the properties of the particles involved. It is not that virtual photons have tiny moods and decide whether to pull or push. The field interaction follows rules, and the virtual particle description keeps track of how those rules affect the result. The strong force is even more interesting. It binds quarks together inside protons and neutrons, and it also helps hold atomic nuclei together. The particles associated with the strong force are called gluons, a name that is almost too charming for one of the most powerful interactions in nature. Gluons are related to a property called color charge. This has nothing to do with visible color. Quarks are not actually red, green, or blue like tiny festive lights. The names are labels for a kind of charge involved in the strong interaction. The strong force is described by a quantum field theory in which quarks exchange gluons. Here the story becomes stranger than electromagnetism. Photons do not carry electric charge, so they do not directly attract or repel other photons in ordinary conditions. Gluons, however, carry the very kind of charge involved in the strong force. That means gluons interact with other gluons. The force carriers themselves participate in the force. This makes the strong force intensely complicated. It also helps explain why quarks are confined inside particles, like protons and neutrons. Try to pull quarks apart, and the field between them does not simply fade away like the electromagnetic force does with distance. Instead, energy builds in the field, and eventually it becomes favourable to create new particles rather than isolate a single quark. The universe seems to say, in effect, you may rearrange these quarks, but you may not have just one to take home. Virtual gluons are used to describe the strong interactions inside protons and neutrons. But again, we should avoid picturing a proton as a tidy bag containing 3 quarks, calmly tossing gluons back and forth like office workers passing notes. A proton is a seething quantum system. Its internal structure includes quarks, gluons, and temporary quark-antiquark contributions, all described through the dynamics of the strong field. Most of the proton's mass does not come directly from the bare masses of its quarks. It comes from the energy of the strong field and the motion and interactions inside the proton. That is a remarkable fact. The matter in your body owes much of its mass not to little solid beads, but to the restless energy of fields binding quarks together. Virtual particles are part of how physicists describe that restless internal life. They help account for the forces and interactions that make protons stable, nuclei possible, and atoms meaningful. But no one should imagine that the inside of a proton is filled with ordinary little particles following neat paths like planets around a sun. It is a quantum field system, and virtual particle language is one way of organizing its complexity. Useful, powerful, and not to be mistaken for a tiny mechanical clockwork. The weak force adds another layer. It is responsible for certain types of particle decay, including processes that allow unstable particles to transform into other particles. It plays an essential role in radioactivity and in the nuclear reactions that power stars. The weak interaction is mediated by heavy force carriers. Because these carriers are massive, the weak force acts only over extremely short distances. In virtual particle language, the heaviness of the mediator limits how far its influence can effectively reach. The weak force is not weak because it is unimportant. It is weak in many ordinary situations because its range is tiny, and its effects are usually hidden, unless particles come very close, or a decay process is possible. This gives us a useful comparison among forces. The electromagnetic force has a massless mediator, the photon, and it can reach across large distances, though its strength weakens with distance and charges can cancel one another in neutral matter. The strong force has gluons and behaves in a very different way because the gluons interact with each other and confinement dominates at larger distances inside nuclear matter. The weak force has heavy mediators and therefore a very short range. Virtual particles help describe all of these differences. They do not do so as little classical messengers with identical jobs, but as internal features of the quantum field interactions that determine how forces behave. There is an important reason force range is often discussed in terms of virtual particles. If a mediator is massless, as with a photon, the associated force can extend very far. If a mediator is heavy, as with the weak force, the associated influence falls away quickly. A loose popular explanation might say that heavy virtual particles are harder to borrow, so they cannot travel far. That phrase has the same problem as the borrowed energy story. It is memorable, but too literal. The more careful explanation is that the properties of the field and its mediator determine how the interaction changes with distance. The virtual particle description encodes that behavior in the calculation. No tiny heavy object is struggling to make the journey before its loan expires. The mathematics of the field sets the range. This is one of the main ways virtual particles shape real forces. Their properties inside the theory are tied to the observable behavior of the force. The type of virtual mediator matters, its mass matters, its charge matters, its interactions with itself and other fields matter. Change those features and the force would be different. The world would be different. Atoms might not form, stars might not shine, matter might not hold together. A small change in the rules of the mediating fields would lead to a universe with very different habits, and possibly much less furniture. Still, it remains true that we never directly observe the virtual exchange itself. What we observe are the outcomes. We observe particles scattering, we observe decays, we observe bound states, we observe spectra, magnetic properties, nuclear behavior, and the stability of matter. The virtual particle framework is successful because it connects the field rules to those outcomes. It tells us what should be likely, what should be rare, what should happen quickly, and what should almost never happen at all. Another way virtual particles shape forces is through corrections. In a simplified first calculation, two charged particles might exchange one virtual photon. That gives a basic result, but quantum field theory does not stop there. More complicated internal processes can also contribute. A virtual photon might briefly produce a virtual electron and its antimatter counterpart in the calculation, then recombine. Additional virtual photons can appear in more detailed diagrams. The theory includes layers of possible internal contributions. Each layer makes a smaller correction in situations where the method works well, and adding them improves the prediction. This is where the force stops being a single clean exchange and becomes a whole set of quantum possibilities. The observed interaction is the result of all relevant contributions combined. The simplest diagram gives the main effect. More complicated diagrams refine it. Physicists add these corrections to predict real measurements more accurately. This is one reason quantum electrodynamics became famous as one of the most precise theories ever made. It does not merely say electrons repel, it predicts tiny details of how they interact, and those details match experiments to an astonishing degree. These corrections also mean that a particle is never entirely alone. An electron, for example, is surrounded in the theory by its interactions with quantum fields. Virtual photons and other virtual processes contribute to its measured properties. This does not mean the electron is literally wearing a fuzzy coat of tiny particles in the everyday sense, though people sometimes speak of a dressing around the particle. It means the electron we measure includes the effects of its interactions with the fields. The bare electron of an idealized starting point is not what we actually observe. The observed electron is shaped by the quantum fields around it. This idea may sound odd, but it is deeply important. The properties of particles are not always fixed little labels independent of their surroundings. Measurements can depend on scale, environment, and the influence of fields. In quantum field theory, interactions modify what we observe. Virtual particles are part of the way those modifications are calculated. They help explain why a charge may appear slightly different when probed at different distances, why magnetic properties receive tiny corrections, and why the simple first picture needs refinement. Now, when we say virtual particles help shape real forces, We should not imagine that the virtual particles are more basic than the fields. The fields are the underlying actors in the theory. Virtual particles are a way of describing field interactions when using certain calculation methods. In some cases, especially when interactions are strong or complicated, the tidy virtual particle picture becomes less useful. Physicists may use different tools, such as lattice methods, where the field behavior is studied in another way. The real force does not disappear when virtual particles are not drawn. This tells us again that virtual particles are not little objects required as literal furniture. They are a representation, an extremely useful one in many settings, but still a representation. That does not lessen their role. A representation can be the difference between confusion and calculation. Feynman diagrams, with their internal virtual particles, gave physicists a practical way to handle the complexity of quantum fields. They turned difficult interactions into organized terms. They allowed predictions to be made, checked, refined, and used. The virtual particle is like a carefully chosen word in a language that lets fields speak to experiments. The word is not the thing itself, but without the word we might struggle to say what the thing is doing. It is also helpful to remember that forces in quantum theory are not always separate from particles in the way our everyday categories suggest. In ordinary thinking, particles are things, and forces are what things do to each other. In quantum field theory, both particles and forces arise from fields and their interactions. Matter fields and force fields are part of the same broad framework. The electron field interacts with the electromagnetic field. Quark fields interact with gluon fields. Fields can exchange energy and momentum. What we call a force is the large-scale or measurable expression of those interactions. This is why the table under your hand feels solid. At the microscopic level, the atoms in your hand and the atoms in the table are made of charged particles. The electrons around those atoms interact electromagnetically. Quantum rules also prevent electrons from all collapsing into identical states. The result is resistance. Your hand does not pass through the table because the fields and particles in both objects interact in ways that make such overlap energetically and quantum mechanically unfavourable. In a loose sense, virtual photons are involved in the electromagnetic repulsion between charged constituents. But the real story includes quantum fields, atomic structure, and the exclusion principle. The familiar feeling of solidity is not simple contact between tiny hardballs. It is the macroscopic result of field interactions and quantum rules. That is worth appreciating. Every time you lean on a desk, walk across a floor, hold a cup, or rest your head on a pillow, you are trusting quantum field interactions. The world feels solid because forces work reliably at scales where you never notice the quantum machinery. Virtual particles are part of the language that explains that machinery. The softness of a blanket and the hardness of a stone both depend, deep down, on electromagnetic interactions among atoms, shaped by quantum rules. The universe has converted field behavior into bedtime furniture, which is one of its more practical achievements. Forces also build structure. Electromagnetism allows atoms to bind into molecules. The strong force holds nuclei together against the electromagnetic repulsion between protons. The weak force allows transformations that are essential in stars and radioactive processes. Gravity, which does not fit neatly into the same quantum framework in the fully complete way physicists would like, shapes planets, stars, galaxies, and the large-scale universe. Virtual particles are central in the quantum descriptions of the non-gravitational forces, and hypothetical virtual gravitons are sometimes discussed in attempts to think quantum mechanically about gravity, though a complete theory of quantum gravity remains unfinished. This unfinished status is another reminder to be careful. Virtual particles are incredibly successful within quantum field theories that have been tested, but they are not magic keys that unlock every door. They are tools within a framework. When the framework is well established, as with the electromagnetic interactions, the tool is extraordinarily powerful. When the framework is incomplete or extremely difficult, as with quantum gravity or strongly interacting systems, the tool may need to be supplemented or replaced by other methods. Physics is not one picture repeated everywhere. It is a set of carefully tested ways of speaking about nature, each with its proper domain. The deeper lesson is that forces are not merely things pushing things. They are patterns of interaction in fields, constrained by symmetries, charges, masses, and quantum rules. Virtual particles help make those patterns calculable. They show how influence can pass through a field without requiring a classical object to travel from one particle to another. They let physicists compute not only the main force, but also the tiny corrections that reveal the vacuum's response. They help connect the unseen internal structure of interactions to the visible behaviour of matter. And this is where the next idea begins to appear naturally. If virtual particles help mediate forces, they also imply that the vacuum around a particle is not passive. A charged particle can disturb the quantum field surrounding it. The vacuum can respond in a way that slightly screens or modifies the charge we measure. It is as if the emptiness near a particle becomes subtly polarized, not with little beads lining up in a simple classical way, but through the response of quantum fields. This effect is called vacuum polarization, and it shows even more clearly how the so-called empty background can alter the properties of real particles and real forces without ever becoming a crowd of ordinary detectable particles. The idea that a force can be shaped by something we cannot directly see is already strange enough, but vacuum polarization asks us to go one step further. It asks us to imagine that empty space does not merely sit quietly around a particle, like a dark room around a candle. Instead, the vacuum responds. Place an electric charge into it, and the surrounding quantum fields adjust. Not in the way a crowd moves aside for someone walking through a hallway, and not in the way water ripples when a stone is dropped into a pond, but in a subtler quantum way. The vacuum becomes slightly altered by the presence of the charge. It develops a kind of invisible structure around it, and that structure changes how the charge is seen by other particles. At first, this sounds almost too much like giving empty space a personality. The vacuum responds, the vacuum screens, the vacuum dresses a particle. These are common phrases, but they can make it sound as though emptiness is leaning forward, thinking things over, and deciding how to behave. That is not what physicists mean. The vacuum is not conscious, not active in a human sense, and certainly not sitting there with a tiny clipboard taking notes on passing electrons. What they mean is that quantum fields have rules, and when a charged particle is present, those rules produce measurable changes in the field state around it. The vacuum near the particle is not the same as the vacuum far away from it. To understand why, let us start with a familiar picture from ordinary electricity. Imagine a positive electric charge placed inside a material, such as a piece of glass or water. The material is made of atoms and molecules, and those atoms and molecules contain positive and negative charges. When the external charge is placed nearby, the charges inside the material shift slightly. Negative parts may be drawn a little closer. Positive parts may be pushed a little farther away. The material becomes polarized. It does not become fully charged overall, but its internal charges rearrange. This rearrangement changes the electric field that other objects feel. The original charge appears partly screened by the response of the material around it. That is ordinary polarization in matter. Vacuum polarization is not the same thing, because the vacuum is not a material made of atoms. There are no little molecules of nothing lining up in rows. But quantum fields can still respond in a way that is mathematically and physically similar enough to earn the name polarization. Around a charged particle, the quantum vacuum behaves as though it can form a subtle cloud of response. In the language of virtual particles, a photon moving through the vacuum can briefly contribute to virtual pairs of particles and antiparticles, such as electrons and positrons, which then recombine. Around an electron, virtual pairs can influence how the electron's charge appears at different distances. The words briefly and pair are again part of the calculation language, not a little movie we should take too literally. but the picture helps point toward a real effect. The vacuum is not completely inert. A positron is the antimatter counterpart of the electron. It has the same mass as an electron but the opposite electric charge. In the virtual particle picture, the electric field of an e-electron influences the possible virtual electron-positron pairs around it. The positive members of these virtual pairs are attracted a little toward the electron, while the negative members are pushed a little away. The result is a screening effect. From a distance, the electron's charge appears slightly reduced because the surrounding vacuum response partially masks it. If another particle probes the electron from far away, it does not see only the bare charge, it sees the charge together with the vacuum's response. This is where the idea of a dressed particle becomes useful. A real electron is not simply the bare object one might first write into a basic theory. It is accompanied by its interactions with the quantum fields around it. Those interactions contribute to the properties we measure. The electron is dressed by the vacuum, not in a coat of tiny ordinary particles, and certainly not in anything warm enough for winter, but by the influence of field interactions. The measured electron includes the effects of its relationship with the surrounding quantum fields. Take those effects away in the theory, and you are no longer describing the electron that experiments actually see. The word screening can make this easier. Suppose you are looking at a lamp through a thin fog. The lamp itself has not changed, but the fog affects how its light reaches you. From far away, the lamp may look softer or dimmer than it would in perfectly clear air. If you move very close, you can see more of the lamp's true brightness, because less fog lies between you and it. Vacuum polarization is not fog, and electric charge is not light from a lamp, but the comparison gives the right kind of feeling. The surrounding medium changes what is observed from a distance. In the quantum case, the so-called medium is the vacuum state of fields, and the effect changes how charge appears when measured at different scales. This leads to a remarkable idea. The strength of a charge is not simply one unchanging number that looks exactly the same at every distance. The effective charge can depend on how closely you probe it. Farther away, the vacuum response screens it. Very close in, you penetrate more of that screening cloud, and the charge appears stronger. Physicists describe this by saying that the coupling changes with scale. In everyday words, the interaction strength depends on the distance or energy at which you examine it. The charge is not wandering around changing its mind. The measured effect changes because the vacuum response included in the measurement changes with scale. This is a very important point, because it shows that empty space does not merely host forces, it modifies them. The electromagnetic force between charged particles is shaped by the behavior of quantum fields in the region around those particles. A simple picture says charge creates a field and another charge responds. A more complete quantum picture says the field itself is affected by vacuum fluctuations, and this changes the observed interaction. The vacuum is not an empty hallway through which forces pass untouched. It is part of the structure of the force. The phrase virtual particles becomes useful here, but once again it must be used with care. In a diagram, vacuum polarization is often shown as a photon that turns into a loop of virtual electron and positron before becoming a photon again. That loop represents the effect of charged particle fields on the propagation of the electromagnetic interaction. It is a compact way of saying that the vacuum can momentarily respond through the fields associated with charged particles. But the loop is not a literal picture of a tiny electron and positron popping out, taking a circular stroll, and then disappearing with good manners. It is a mathematical contribution. The measured result is real, but the internal image is a tool. What does that real result look like? It can appear as a tiny modification of atomic energy levels. It can appear in precision measurements of how particles scatter. It can appear in the way the strength of the electromagnetic interaction changes at very small distances. In each case, the basic point is the same. The vacuum response alters what we measure. The correction may be small, but small corrections are often where modern physics shows its sharpest teeth. A large, obvious effect can sometimes be explained in many ways. A tiny effect predicted correctly to high precision is much harder to dismiss. It means the theory has reached into the quiet details and come back with the right answer. Vacuum polarization also helps us understand why the term vacuum should not be taken to mean nothing in the ordinary sense. A classical vacuum has no air. A quantum vacuum has no real particles, but it still contains the fields and their ground state behavior. Those fields can respond to the presence of charges. The response is not optional. It follows from the structure of the theory. Once charge fields exist, and once the electromagnetic field interacts with them, the vacuum cannot remain a perfectly featureless backdrop around a charge. It is changed by the possibility of those interactions. There is a subtle but useful distinction between saying virtual pairs exist in the vacuum and saying the vacuum has the capacity to respond through quantum fields. The first statement can encourage a mental picture of countless little particles hiding everywhere. The second statement is less visual, but more accurate. The vacuum is the lowest energy state of the fields. When a charge or a field disturbance is present, the quantum fields contribute corrections to the interaction. Virtual pairs are one way to organize those corrections. They are not independent residents of space. They are part of how the theory represents the response. This invisible response becomes even more striking in strong fields. When electric fields become extremely intense, the distinction between virtual possibilities and real particle production can become important. Under ordinary conditions, the virtual contributions remain internal to interactions. But if a field is strong enough, it may provide enough energy for real particle pairs to be created. That is a different situation from vacuum polarization alone. In that case, real particles could in principle be observed. This distinction matters because it prevents us from mixing together two related but different ideas. Virtual effects modify interactions without producing free detectable particles. Real pair production creates actual particles that can be measured as outgoing states. The vacuum can participate in both stories, but the stories are not the same. A careful way to say it is this. Vacuum polarization is not the vacuum constantly producing matter out of nowhere. It is the quantum fields altering the behavior of interactions because the vacuum state is affected by the presence of fields and charges. Matter does not simply appear as free particles unless the physical conditions allow it. Conservation laws still apply. Energy still has to come from somewhere for real particles to be produced. The virtual particle description is not a license for the universe to manufacture electrons whenever it feels decorative. There is an old desire in human thinking to imagine space as a container and particles as objects inside it. The container is empty or full. The objects are present or absent. Vacuum polarization gently breaks that container picture. It says the fields are not simply inside space in the way furniture is inside a room. They are part of what physical space contains at every point, even when no particles are present. A charged particle is not merely placed into empty nothing. It is an excitation of one field interacting with other fields, and those interactions reshape the conditions around it. The particle and its surrounding field response form the thing we actually measure. This is why physicists sometimes speak of the bare charge and the observed charge. The bare charge is a parameter in the theory before certain effects are included. The observed charge is what experiments actually infer after all the vacuum response has done its work. The bare object is not something you can simply peel out and place on the table. It is part of the theoretical setup. The observed particle is always already involved with the fields. If that sounds philosophically annoying, it is also experimentally necessary. Nature does not hand us isolated ingredients with labels. It gives us interacting systems. The same broad idea appears in other forces too, though the details differ. In the strong force, the vacuum response behaves in a very different way from electromagnetism. Instead of screening color charge in the same simple style, the self-interactions of gluons lead to behavior where the force becomes weaker at very short distances and stronger at larger ones. This is one of the reasons quarks behave almost freely when probed extremely closely inside protons, yet cannot be isolated at ordinary distances. The vacuum response is not a universal fog that always softens everything. It depends on the field, the charges involved, and the way the force carriers interact. Different quantum fields give the vacuum different habits. That is a remarkable thought. The vacuum is not just one simple background with one simple response. It responds according to the fields involved. For electromagnetism, charge-particle pair screen. For the strong interaction, the field's own self-interaction changes the story dramatically. The vacuum is more like a complicated physical state whose behaviour depends on which part of the theory is being disturbed. It is not a passive emptiness. It is the quiet version of all the fields, and each field has its own rules for how quiet can be. This idea has deep consequences for how physicists understand the apparent strength of forces. When experiments probe smaller distances, they are not merely looking closer in the way a magnifying glass looks closer at a printed page. They are testing the interaction at higher energy scales. At those scales, the vacuum response can look different. The effective force can change. This scale dependence is not an experimental nuisance. It is a major clue about the underlying theory. By measuring how interactions change with scale, physicists learn about the fields and virtual contributions that shape them. In this sense, vacuum polarization turns empty space into a kind of diagnostic surface. Not a surface you can touch, but a responsive background whose effects reveal what fields exist and how they interact. If only electrons existed, the vacuum response would look one way. If heavier charged particles also exist, they can contribute at scales where the energy is high enough for their effects to matter in the calculations. Even particles too heavy to appear directly in a low-energy experiment can sometimes leave subtle fingerprints through virtual effects. This is one of the ways physics can sense the presence of deeper layers before directly producing new particles. The vacuum response carries clues. There is a nice detective story hidden here. Suppose you cannot see a creature directly, but you notice how the grass bends, how the water ripples, and how the birds suddenly become suspicious. You infer that something is there. In particle physics, virtual effects can play a similar role. The direct particle may not appear in the detector, perhaps because the experiment does not have enough energy to create it as a real particle. But its field can still contribute indirectly to measurable quantities. The vacuum response is one place where the hidden structure of the theory can leave signs. The signs are subtle, and they require careful interpretation, but they're real enough to guide discovery. This is one reason physicists care so deeply about precision. High-energy collisions are dramatic, but precision measurements are quiet and powerful. A tiny deviation from the expected value of a magnetic moment, an atomic transition, or a scattering rate can hint that some virtual contribution has not been accounted for. Maybe the known fields explain it. Maybe there is a calculation error. Maybe the experiment has an unrecognized systematic effect. Or maybe, very rarely and very excitingly, there is new physics. The vacuum response becomes a place where the known and unknown negotiate in decimals. For a sleep-friendly journey, we do not need the technical machinery behind all of this. We only need the core idea. The vacuum around a charge is not a featureless void. Quantum fields respond to that charge. In the virtual particle language, this response can be pictured as pairs appearing in the calculation and partly screening the charge. The result is that the force between particles is slightly altered, and the apparent strength of the interaction can depend on the scale at which it is measured. This is vacuum polarization. It is invisible in daily life, but it is not optional in accurate physics. It also gives us a more refined answer to the original question. Virtual particles are not real as free detected particles, but the processes represented by virtual particles correspond to real changes in field behavior. Vacuum polarization is one of the clearest examples. The virtual pairs in the diagrams are not little creatures swarming around an electron, yet the vacuum response they represent changes measurable interactions. The diagrams are not literal photographs, they are reliable maps, and as with all good maps, the point is not to confuse the ink for the landscape, but to recognise that the map can guide us through terrain we cannot see directly. There is something quietly humbling about the fact that an electron is not just an electron in isolation. It is an electron plus the effect of the fields with which it interacts. Even the simplest particle is part of a wider quantum environment. The vacuum, far from being a blank nothing, helps define what the particle looks like to the rest of the universe. A charge is measured through its interactions, and those interactions include the vacuum's invisible response. Nothing once again turns out to be not quite nothing. This also changes the meaning of measurement. When we measure a particle's charge, we're not reaching into nature and pulling out a tiny engraved number from the particle's surface. We're observing how it behaves in interactions. We infer the charge from the way it pushes, pulls, scatters, binds, or shifts energy levels. If the vacuum modifies those interactions, then the measured charge includes that modification. Measurement is not a pure act of looking, it is participation in a system of fields. The same lesson applies more broadly. Many properties in modern physics are not isolated possessions, they are relational. They show themselves through interactions. Mass, charge, spin, magnetic behaviour, decay rates, scattering probabilities, all are known through what systems do. Virtual particles matter because they appear in the calculation of what systems do. They belong to the hidden grammar connecting one observable event to another. We cannot point to them as little objects in the middle, but we can see the sentence they help write. Vacuum polarization is therefore not just a technical correction. It is a window into the deeper character of reality. It says that empty space has structure, that fields respond to presence, that particles are shaped by their interactions, and that the visible properties of matter include invisible contributions. The universe is not assembled from isolated pieces sitting in a neutral void. It is an interacting whole, where even the quiet background participates according to quantum rules. And from here, the path leads naturally toward the question of evidence. It is one thing to say that the vacuum responds, it is another to show how such invisible responses leave measurable footprints. Some of those footprints are found in atoms where energy levels shift by tiny amounts. Others appear in the magnetic behaviour of particles, where the simplest prediction is not quite enough. Others emerge in high-precision scattering experiments, where the strength of a force changes with scale. These are the places where mathematical ghosts, the virtual particles that cannot be caught directly, leave marks on instruments that very much can be read. The strange thing about virtual particles is that they are most convincing when no one tries to catch them directly. That sounds backwards, because most of the time in science, if we want to know whether something is real, we try to observe it. We point a telescope at a galaxy. We place a detector beside a beam of particles. We look for a track, a flash, a click, a signal, something that says, yes, something passed through here. But virtual particles do not cooperate with that kind of investigation. They do not stroll into a detector and announce themselves. They do not leave a neat little mark with their name attached. They are not the actors walking on stage under the lights. They are more like the hidden stage directions, never seen by the audience but somehow responsible for the timing of every entrance, pause, and turn. And yet the audience can tell when the directions are there. This is where the whole subject becomes both delicate and powerful. If virtual particles are only internal features of calculations, why do physicists speak about them with such confidence? Why not simply say they are convenient fiction and move on? The reason is that the calculations in which they appear do not merely give rough guesses, they produce predictions that match the measured world with extraordinary precision. The virtual particles themselves are not observed, but the changes associated with their effects are observed. The ghosts do not appear in the photograph, but the furniture is moved. One of the cleanest examples comes from atoms. Atoms are often introduced as little solar systems, with electrons circling a nucleus like planets around a star. That picture is charming, and it still sneaks into textbooks and classroom posters, usually with brightly coloured spheres that look very pleased with themselves. But real atoms are quantum systems. Electrons in atoms do not orbit like tiny planets. They occupy allowed states described by quantum rules. Those states have specific energy levels, and when electrons move between them, atoms absorb or emit light with precise colours. By measuring those colours very carefully, physicists can infer the spacing of the atomic energy levels. For a long time, the basic quantum theory of the hydrogen atom gave remarkably good predictions. Hydrogen is the simplest atom, just one proton and one electron, which makes it the physicist's favourite kind of thing, a system simple enough to calculate and real enough to test. But when measurements became more precise, tiny differences appeared. Certain energy levels that were expected to match exactly were found to be slightly separated. The difference was small, almost absurdly small by everyday standards, but it was real. Instruments could measure it. The atom was whispering that the simple theory had missed something. That tiny shift is known as the Lamb shift, named after the physicist Willis Lamb, who helped measure it. The explanation comes from quantum field theory. The electron in the hydrogen atom is not sitting in a passive empty background. It interacts with the electromagnetic field, including the field's vacuum fluctuations. In the language of virtual particles, the electron can emit and reabsorb virtual photons, and the vacuum can respond through virtual particle pairs. These effects slightly alter the electron's behaviour inside the atom. The result is a tiny shift in energy levels. No one sees a virtual photon dart away from the electron and return like a nervous messenger. No one watches a virtual pair appear between the electron and the proton. But the energy levels move by just the amount the theory predicts. The light emitted by hydrogen carries the evidence. The atom becomes a precision instrument, and its spectrum becomes a record of quantum field effects. This is one of the great lessons of modern physics. Invisible corrections can become visible as tiny differences in measured light. The Lamb shift is a beautiful example because it shows how the vacuum is not just a background word. It affects the structure of an atom. Empty space, in the quantum sense, helps determine the exact colours of light that atoms can emit. That sentence should be allowed to sit quietly for a moment. The colour of light from hydrogen, one of the most basic features of the universe, is shaped not only by the electron and proton, but by the restless structure of the vacuum around them. The mathematical ghosts leave their footprint in the spectrum. Another famous footprint appears in the magnetic behaviour of the electron. Electrons behave as though they carry a tiny magnet with them. This magnetic property can be measured with astonishing care. Early quantum theory predicted a basic value for it, and that value was close. But close was not enough, because experiments showed a slight difference. Quantum field theory explained that difference by including the effects of interactions with the electromagnetic field. In the diagrams, the electron interacts with virtual photons, and more complicated virtual processes add tiny corrections. The result is a prediction so precise that it has become one of the great triumphs of theoretical physics. Again, nothing in this means that a detector has caught the virtual particles surrounding the electron. The correction is not a little swarm photographed around it. It is a change in the measured magnetic behaviour. The electron's magnetism is not quite what the simplest theory says it should be. It is shifted by the influence of quantum fields. The virtual particle diagrams organise those shifts. When the calculation agrees with the experiment to many decimal places, the ghosts may remain unseen, but their handwriting is unmistakable. This is also why precision can be more powerful than drama. A particle collision in a giant machine is dramatic. Beams racing in opposite directions, detectors the size of buildings, showers of particles, mountains of data. It has the feeling of a grand scientific event, and it is, but a quiet measurement of a small magnetic property can be just as profound. If the theory predicts the value and the experiment confirms it, then the hidden quantum corrections have been tested. If the value differs, something is missing. Either the calculation is incomplete, the experiment has an unnoticed complication, or nature is hinting at a field or particle not yet understood. Tiny numbers can be doors. This is one reason physicists care about measurements that seem, to most people, almost comically precise. Why worry about the last few decimal places of a particle's magnetic moment? Why measure atomic light so carefully that ordinary language runs out of comfortable adjectives? Because the small differences are where virtual effects live. The large obvious behaviour is often explained by the simplest parts of the theory. The hidden parts reveal themselves as corrections. If you want to find the influence of something that cannot be directly observed, you look for the places where reality fails to match the simplified picture by just a little. There is a gentle analogy in music. If someone plays a familiar melody on a piano, you can recognize it immediately. But a trained tuner hears more. They hear that one string is slightly sharp, another slightly flat. One note rings longer than expected, another has a faint buzz. The melody is obvious to everyone, but the tiny deviations reveal the structure of the instrument. Precision physics listens to nature in that way. The main tune tells us the broad theory is right. The tiny shifts tell us what is happening inside the instrument. Particle scattering offers another kind of footprint. In scattering experiments, physicists send particles toward one another and study how they emerge. They may bounce away at different angles, produce other particles, or transfer energy and momentum in particular patterns. The probabilities of these outcomes are the things the theory must predict. Virtual particles appear inside the calculations as mediators and corrections. A simple interaction may involve one virtual exchange. A more accurate calculation includes additional virtual processes. Each contributes a little to the final probability. This is not unlike predicting where ripples will go after several stones are dropped into a pond, except the pond is a quantum field, the stones are particles, and the ripples are not obliged to respect ordinary intuition. The detector sees the final outgoing particles. It does not see every internal contribution. But the pattern of outcomes contains the combined effect of those contributions. If virtual processes are included properly, the predicted pattern matches the measured one. If they are ignored, the prediction is incomplete. This is how mathematical ghosts become experimentally accountable. They may not be directly observable, but they influence observable probabilities. They alter how often one outcome occurs compared with another. They change the angle of scattering, the rate of decay, the strength of an interaction, or the energy of a state. Nature does not label the contribution, but it adds it to the total. Another important footprint is the way forces change with distance or energy. Earlier we spoke about vacuum polarization, where the vacuum responds to a charge and changes how that charge appears at different scales. This means that the strength of a force is not always fixed in the naive sense. If you probe very close to a charged particle, you see through more of the vacuum screening. If you observe from farther away, the response of the vacuum affects what you infer. Experiments confirm that interaction strengths depend on scale in ways predicted by quantum field theory. This idea sounds strange only because everyday life hides it from us. When you pick up a cup, the electromagnetic interactions between atoms behave in a way that feels perfectly stable. You do not notice any scale-dependent subtleties. The cup does not become metaphysically uncertain halfway to your mouth, which is good, because tea already has enough ways to cause trouble. But in high-energy experiments where particles are probed at extremely small distances, the changing strength of interactions matters. The vacuum's invisible response becomes part of the measured behaviour. Virtual particle contributions help calculate this change. The strong force gives a particularly striking example. At very short distances, quarks inside protons and neutrons behave almost as if they are free. At larger distances, the strong force becomes confining, preventing quarks from being isolated. This unusual behaviour is tied to the quantum structure of the strong field and the way its force carriers interact with themselves. The vacuum response in this theory is very different from the electromagnetic case. It is not merely a softer version of the same idea. It is a different kind of field with different rules. and the measurable behavior of quarks reveals those rules. Once again, the hidden field dynamics leave footprints in real experiments. Particle decays provide yet another route. Some particles are unstable. They transform into lighter particles after a certain average time. The weak force is often responsible for these transformations. Virtual particles appear in the calculation of many decay processes, especially when a particle changes type through an interaction that cannot be described as a simple direct splitting. The rate of decay, the identities of the products, and the distribution of their energies all carry information about the internal process. Detectors record the final particles. The theory uses virtual mediators to connect the initial particle to the final ones. A decay rate may sound less tangible than a force, but it is a powerful measurement. If a particle decays too quickly or too slowly compared with prediction, the theory must explain why. If a rare decay happens more often than expected, it may indicate that additional virtual contributions are present. This is one of the ways physicists search for new physics. They do not always need to create a new particle directly. Sometimes they look for the shadow it casts inside a process it can influence virtually. This shadow language is helpful. Suppose a person walks behind a paper screen. You cannot see the person directly, but you see the screen move, you see the outline bend and shift. You infer a presence from its effect. In particle physics, a heavy particle might be too difficult to produce directly in a given experiment. But if it interacts with known particles, it may still affect certain measured quantities through virtual contributions. The effect may be tiny, and many other explanations must be ruled out, but the principle is clear. The unseen can sometimes be inferred by the precision of its shadow. This is why the word ghost feels appropriate, though only as a metaphor. Virtual particles haunt the calculations, not the laboratory. They are not supernatural, and they are not optional decorations. They are internal contributions that can change measurable outcomes. Their footprints are not ectoplasm on the floor, thankfully, but shifts in spectra, corrections to magnetic properties, altered scattering probabilities, scale-dependent forces, and decay rates. If one knows how to read these marks, they tell a consistent story. There is a practical humility in this. Physicists do not say we believe in virtual particles because we like the picture. They say this formalism using virtual particles predicts what experiments measure. The belief is not in the cartoon, but in the tested structure. When the same framework explains many different effects across many different systems, confidence grows. The language of virtual particles earns its place not by being easy to imagine, but by being useful, precise, and repeatedly confirmed through its consequences. Still, we should not confuse confirmation of the theory with confirmation that every diagram is a literal event. This is a subtle point and worth returning to softly. A Feynman diagram can represent a contribution to a process. Many diagrams may contribute to the same process. Depending on how the calculation is organized, the internal picture can look different while the final observable prediction remains the same. The measurable footprint is real. The full field interaction is real. The diagram is a representation of one part of the calculation. If we take it as a tiny documentary film, we ask the wrong questions. Imagine an architect's drawing of a building. The drawing may include guidelines, construction marks, labels, and perspectives that do not appear in the finished structure. Those marks are not part of the building, but they help produce a correct plan. If the building stands exactly as predicted, the drawing has been validated as a tool. But no one expects to find the guidelines floating inside the walls. Virtual particles are guidelines of a very sophisticated kind. They organize the construction of predictions. The finished building is the measured world. The remarkable part is how many buildings they help construct. Atomic physics, particle scattering, magnetic moments, decay processes, vacuum effects, and the behavior of forces all carry marks that quantum field theory explains through virtual contributions. This gives virtual particles a strange status. They are not real like particles that hit detectors. They are not unreal like made-up creatures in a bedtime story. They are part of a mathematical structure so tightly connected to measurement that dismissing them as mere fiction would be misleading. They are not the furniture, but the furniture is arranged according to plans in which they appear. This is also a good place to remember that physics often lives with layers of reality. Some things are directly observed, some are inferred, some are model dependent, some are useful only within a chosen approximation. The skill is not to force all of them into one category, but to understand what kind of claim is being made. A real photon from a lamp can be detected. A virtual photon exchange between electrons cannot be detected in the same way. The electromagnetic interaction, however, is real. The calculation using virtual photons predicts that interaction. The footprint belongs to the interaction, and the virtual photon belongs to the language that describes it. The deeper we go, the more important this distinction becomes. In ordinary life, we may not care whether a concept is directly real or just a useful part of a model, as long as the lights turn on when we flip the switch. But in foundational physics, these distinctions matter. They stop us from saying too much. They keep wonder tied to evidence. They allow us to say that virtual particles change reality only in a careful sense. They change our calculated predictions of reality because they represent real field interactions, and those predictions match real measurements. But they are not little independent objects secretly carrying out tasks behind the curtain. There is something satisfying about that carefulness. It refuses both extremes. It refuses the crude claim that virtual particles are simply fake and meaningless. It also refuses the overexcited claim that empty space is literally packed with tiny temporary particles waiting to be caught. The truth sits in a quieter middle. The vacuum has quantum structure, fields interact. Calculations include virtual contributions. Experiments measure the consequences. Reality is changed, or rather revealed, through effects that cannot be understood by looking only at real, incoming and outgoing particles. This is one of the reasons modern physics can feel both precise and dreamlike. It speaks of things that cannot be pictured directly, yet it predicts measurements more accurately than almost any other branch of science. It tells us that the visible world is supported by invisible relationships. It shows that the properties of matter are not simply stamped onto particles in isolation, but shaped by their constant connection to fields. It teaches us that absence can have structure, and that the quietest state of a field can still matter. So when mathematical ghosts leave measurable footprints, the footprints are not vague impressions. They are exact shifts, rates, corrections and patterns. They are the slight movement of an atomic energy level. The tiny adjustment of an electron's magnetic behavior. The altered probability of a scattering outcome. The way a force changes when examined more closely. The rare decay that may carry the influence of something too heavy to appear directly. These are the places where the hidden grammar of the theory becomes readable, and once we accept that, the final question becomes less like a trap and more like an invitation. Are virtual particles real enough? Not real in the ordinary particle sense. Not real like a photon that crosses a room and enters your eye. Not real like an electron track in a detector. But real enough to be indispensable in the way physicists describe interactions. Real enough to organize predictions that match experiments. Real enough that removing their contributions would leave the measured world unexplained. The answer may depend on what kind of reality we're asking for, and that is where the story turns from evidence toward interpretation, from footprints in the laboratory toward the careful meaning of the word real itself. By now, the phrase virtual particle may feel less like a clear label and more like a small doorway into the philosophy department, which is a dangerous place to wander to late at night without snacks. We began with the simple puzzle that if virtual particles are not real, it seems strange that they can help explain real effects. We have seen them appear in the way forces are calculated, in the behavior of the quantum vacuum, in the attraction between close metal plates, in the tiny shifts of atomic energy levels, and in the precise magnetic properties of particles. They cannot be caught directly, and yet the calculations that include them keep agreeing with nature. They are not ordinary particles, but they are not useless inventions either. So the question becomes softer, more careful, and more interesting. Are virtual particles real enough? That phrase, real enough, may sound like a compromise, as if we are letting virtual particles into reality through a side door because they brought a convincing letter of recommendation. But physics often works with different kinds of reality. Some things are real because they can be observed directly. A flash of light in a detector, a track left by a charged particle, a planet crossing a telescope's field of view. These are the easy cases. Other things are real because they are inferred from patterns. We do not see the wind itself in the same way we see a tree, but we see leaves moving, dust rising, clouds shifting, and umbrellas turning inside out at exactly the wrong moment. The wind is not less real because we know it through its effects. Much of science is built on this kind of inference, but virtual particles are subtler even than that. They are not inferred as hidden objects in quite the same way the wind is inferred from moving leaves. A virtual photon exchange between two electrons is not simply an invisible little object whose path we fail to record. It is an internal part of the calculation that describes the electromagnetic interaction. It belongs to the way quantum field theory organizes the relationship between the real particles that enter an experiment and the real particles that leave it. If we try to treat it as a tiny thing with a definite little journey, we make the idea too classical, too ordinary, too much like a bead travelling through space. And quantum theory, as it has politely reminded us many times, did not come all this way merely to behave like beads. A useful way to approach the question is to ask what we need a particle to do before we call it real. A real particle can appear as an incoming or outgoing state. It can be emitted, travel, interact, and be detected. Be. It can leave a measurable record. A photon from a lamp can cross the room and enter your eye. An electron can pass through a detector and leave a track. These particles satisfy the rules required for free observable particles. Virtual particles do not. They live inside the interaction, not at the edges where measurement begins and ends. They do not appear as final detected objects. They are not free travellers. They are more like the hidden grammar of the process. Grammar is a helpful comparison because grammar shapes meaning without being a separate character in the story. If you read a sentence, you do not meet the grammar as a person, standing between the words, wearing a small hat and giving instructions. Yet without grammar, the sentence falls apart. The meaning depends on structure. Virtual particles are something like grammatical elements in the language of quantum fields. They are not the measured events themselves, but they help connect measured events into a coherent prediction. They tell the calculation how interactions can contribute, how probabilities are shaped, how fields influence one another. This is why saying virtual particles are not real can be true and misleading at the same time. It is true if real means directly detectable as an independent particle. It is misleading if it suggests they are merely decorative, arbitrary, or fictional in a careless sense. They are not little pieces of matter hiding in the vacuum, but neither are they random doodles in a physicist's notebook. They arise from a deeply tested framework. Remove their contributions, and many precise measurements no longer make sense. The world we measure seems to require the effects they represent, even if it does not require us to imagine them as tiny objects flitting around behind the curtain. The more grounded statement is that the underlying quantum fields are real, in the sense that they successfully describe the behavior of particles and forces. Virtual particles are one way of representing the internal behavior of those fields during interactions. When the representation is used correctly, it predicts real outcomes. That is the key. The virtual particle itself is not necessarily a piece of furniture in the universe. It is part of the blueprint used to understand how the furniture is arranged. The furniture is real. The blueprint is not the furniture. But a correct blueprint is not meaningless. This distinction may feel fussy, but it protects us from two mistakes. The first mistake is to believe too little, to dismiss virtual particles as if they were merely imaginary and therefore irrelevant. that misses the fact that virtual particle calculations explain measurable effects with remarkable precision. The second mistake is to believe too literally, to picture the vacuum as a crowded swarm of temporary particles popping in and out like bubbles in boiling soup. That picture can be comforting because it gives us objects, and humans do love objects. But it is not the deeper view. The deeper view is field behaviour, interaction, uncertainty and calculation. The word real has always been more complicated in physics than it seems in daily life. An electric field is real, but you cannot hold a handful of it. A magnetic field is real, though it becomes visible mostly through what it does to matter, light, and moving charges. The curvature of space-time is real, but no one finds a wrinkle of it folded in a drawer. Temperature is real, but it is not a substance inside warm tea. It emerges from the motion and energy of many particles. A sound wave is real, but it is not a thing separate from the air, water, or material through which it travels. Reality includes objects, but it also includes patterns, states, relationships, and structures. Virtual particles sit near the edge of that list. They are not patterns in the same simple way as sound waves, but they are part of a mathematical structure tied to observable patterns. They are not directly detected entities, but they are not arbitrary labels either. Their reality is not object reality. It is calculational and relational reality. That phrase may sound a little stiff, so we can say it more gently. Virtual particles are real as part of the way fields influence one another, but not real as tiny things you can catch. This is also why different physicists may talk about them differently. One physicist may say virtual particles are not real at all, because only observable particles deserve that label. Another may say they are real enough, because their effects are unavoidable in successful calculations. A third may avoid the argument entirely and say that quantum field theory predicts the measurements, and the words we use are secondary. These are not necessarily disagreements about the experiments. They are disagreements about interpretation and language. Everyone agrees that the measurable effects exist. The debate is about what kind of existence to assign to the internal pieces of the explanation. There is a quiet humility in that. Science is often imagined as a machine for turning mystery into certainty, but in practice it is also a careful discipline of saying exactly what kind of certainty we have. We can be very certain that the calculations of quantum field theory work in tested domains. We can be very certain that the vacuum has measurable effects. We can be very certain that virtual particle diagrams are powerful tools, but we should be cautious about turning those diagrams into literal pictures. The universe is under no obligation to resemble the drawings we use to understand it. A Feynman diagram, after all, looks like a tiny story. Lines come in, lines meet, lines leave. It feels natural to read it as a sequence of little events, but the diagram is not a photograph. It is a compact representation of mathematical contributions. The internal lines are virtual particles. The external lines correspond to real incoming and outgoing particles. The diagram helps us calculate the probability of what can be observed. Its value lies in what it predicts, not in how closely it resembles a microscopic cartoon. It is a map, and a map can be excellent without being the territory. This map has guided physics through some of its most precise successes. It helps explain why atomic energy levels shift slightly from simple expectations. It helps explain why an electron's magnetic behaviour is not quite the first value a simpler theory would suggest. It helps describe how forces are modified by vacuum polarization. It helps predict scattering patterns in particle experiments. It helps organise the hidden contributions that add up to visible outcomes. These are not vague achievements. They are careful, numerical, experimentally tested achievements, though we do not need the numbers here to appreciate the point. The footprints are real, and they match the map. So perhaps real enough means this: virtual particles are real enough to matter in our best descriptions of nature. They are real enough that their associated contributions must be included to match experiments. They are real enough to reveal that empty space has quantum structure. They are real enough to help explain forces, corrections, shifts, and responses, but they are not real enough to be treated as ordinary particles with independent lives. They do not sit in the vacuum waiting to be discovered. They do not zip through space like hidden dust. They are not small residents of nothingness. They are part of how fields do their work in the language of the theory. This answer may feel less tidy than a simple yes or no, but physics often becomes more honest when it becomes less tidy. A rainbow is real, but it is not an object hanging in the sky. It depends on sunlight, raindrops, and the observer's position. Move, and the rainbow moves with you. You cannot walk to the end of it and collect a bright-coloured ribbon. Yet it is not imaginary. It can be photographed. It can be explained. It can brighten an afternoon. Its reality is relational. Virtual particles are not rainbows, but the lesson is similar. Not everything real is real in the same way. A shadow is another useful comparison. A shadow is real enough to cool the ground and show the shape of an object, but it is not a material thing placed on the pavement. It is a pattern created by light being blocked. You cannot pick it up. You cannot weigh it. Yet it belongs to the physical world. Virtual particles are not shadows either, but they too remind us that physical significance does not always require objecthood. Sometimes what matters is a contribution, a constraint, a pattern in a calculation that corresponds to something measurable. The danger, of course, is that this can sound like wordplay if we forget the experiments. Without measurement, one could invent many clever categories of reality and float away into philosophical mist. But virtual particles are tied to experiments. Their value is not that they sound mysterious. Their value is that the theory using them works. When we say they are not real, we are not dismissing their effects. When we say they are real enough, we're not pretending they can be bottled. We're placing them in the right category. This category also helps us understand why empty space is so different from ordinary nothing. The vacuum is not crowded with virtual particles in the literal sense, but it is filled with fields in their lowest energy states. Those fields fluctuate. They respond to boundaries and charges. They mediate forces. They alter measurements. Virtual particles are a way of describing that activity and interactions. The vacuum is quiet, but quiet does not mean featureless. A sleeping city is quieter than a waking one, but its streets, wires, buildings, and hidden systems remain. Empty space is not a city, thankfully, because parking would be impossible, but it too has a structure beneath its silence. This is perhaps the most useful final understanding. The question began with virtual particles, but the real lesson is about fields. Fields are the deep language of modern particle physics. Particles are excitations of fields. Forces are interactions among fields. The vacuum is the lowest energy state of fields. Virtual particles are internal features used when calculating those interactions. Once fields are placed at the centre, the mystery becomes clearer. We stop asking how unreal little objects can push real things around, and we begin asking how quantum fields produce measurable effects. That second question is the one physics can answer with confidence, and still, the first question remains charming, because it captures the feeling of the subject. There is something wonderfully strange about mathematical entities that cannot be caught, but cannot be ignored. They are like the quiet assumptions behind a good story, invisible until you remove them and everything collapses. They show us that reality is not limited to what appears at the surface of measurement. The visible event is only the edge of a deeper process. Behind it lies a structure of fields and possibilities, not directly pictured, yet precise enough to shape the world. This matters beyond particle physics because it changes our sense of what explanation can be. The world is not always explained by finding smaller and smaller solid things. Sometimes it is explained by understanding the rules that connect events. Sometimes the hidden part is not another object, but a relationship. Sometimes the answer is not a bead, but a field. Not a tiny messenger, but an interaction. Not a visible particle, but a virtual contribution that guides the probability of what will be seen. So are virtual particles real enough? Yes, if we mean real enough to be indispensable in the working language of quantum field theory. Yes, if we mean real enough for their associated effects to appear in experiments. Yes, if we mean real enough to remind us that the vacuum is not blank and that forces have quantum structure. But no, if we mean real like little particles flying freely through space, waiting to be captured by a detector. No, if we mean real like a dust grain, a photon from a lamp, or an electron track in a chamber. They belong to a different kind of reality, one step removed from direct observation, but deeply tied to the measurable world. And maybe that is not such a strange answer after all. Much of life is shaped by things we do not hold directly. A promise is not a physical object, but it can alter a life. A memory cannot be placed on a scale, but it can change the course of a day. A rule in a game is not one of the pieces, but without it the pieces have no meaning. Physics is more exact than these human comparisons, of course, and far less likely to become sentimental over tea, but it too contains structures that shape outcomes without being ordinary objects. Virtual particles are among those structures. As we come gently back from the quantum vacuum to the quieter room around you, the world may look almost the same as before. The walls are still walls, the floor still holds you up, the air, if there is air where you are, still rests against your skin. But beneath that ordinary stability is a deeper story. The solidity of matter depends on fields. The forces between particles depend on interactions. Empty space is not truly empty. And some of the most accurate predictions in all of science rely on entities that are not real in the simple, everyday sense, yet are far too effective to be dismissed as unreal. That is the strange comfort of virtual particles. They teach us that the universe is subtle without being vague. It can hide its workings from direct view and still leave precise traces. It can be filled with fields without being filled with stuff. It can use mathematical ghosts to mark real measurements. And it can remind us, very softly, that reality is not always the same as visibility. So wherever you are listening from tonight, whether the room is dark, the hour is late, or the day is only beginning to loosen around its edges, perhaps you can rest for a moment with this thought. Even empty space has depth. Even nothing has rules. Even the unseen can matter. And if you found this journey calming or curious or just strange enough to make the universe feel a little wider and a little quieter, I would be grateful if you liked the video, subscribed, and shared this peaceful corner of physics with someone else who might enjoy drifting through the hidden machinery of reality. The virtual particles themselves will not notice, of course. They are not that kind of real. But the fields will continue their quiet work. The atoms will keep their careful structure. The vacuum will remain not quite empty, and somewhere between what can be measured and what can only be inferred, the universe will keep unfolding with its usual strange precision. Sleep well, fellow traveller, and may your own little corner of reality feel steady, soft, and real enough for rest.